Hello there, and welcome to Physics with William, where curiosity settles into a comfortable chair, the universe lowers its voice a little, and science takes the long, quiet road towards sleep. Tonight, we are going to drift gently toward one of the biggest questions human beings have ever asked, and it is a question so large that it almost feels too big to fit inside a single thought. What actually happened during the Big Bang? Not the cartoon version. Not the dramatic fireball bursting into empty space like a cosmic firework, and not the simple sentence that says everything began with an explosion. The real story is stranger than that, quieter in some ways, far more extreme in others, and much more interesting. It is the story of space itself changing, of time becoming meaningful, of matter appearing from a state so hot and dense that ordinary words begin to struggle. It is the story of how a universe with galaxies, stars, planets, oceans, clouds, clocks, and sleepy listeners could have emerged from conditions that were once smaller, hotter, and more compressed than anything we can directly recreate. Before we begin properly, I would love to ask you something simple. Where are you listening from tonight? And when you look around your little corner of the world, what does the universe feel like right now? Maybe it is late where you are, and the room is dim, and the day has finally loosened its grip. Maybe it's raining softly outside. Maybe there is a lamp beside you, or a cup of tea cooling nearby, or a cat somewhere making a decision that none of us will ever fully understand. Or maybe it is morning, and you're starting your day with a quiet journey back to the very beginning. Wherever you are, you're sitting inside the result of this ancient event. The atoms in your body, the air in your lungs, the light from your screen, the ground beneath your feet, all of it belongs to a universe that was once in a condition so different from the present that it takes some patience to imagine it. And if this kind of gentle science helps you unwind, if the vastness of the cosmos gives your thoughts somewhere calmer to wander, then I would be grateful if you gave the video a like, subscribed, or simply stayed with me for a while. It helps this small, quiet place reach other people who might also enjoy learning about the universe without being hurried through it. There is no need to rush tonight. The Big Bang has already taken its time, nearly 14 billion years in fact, which is an impressive delay by any standard, even for a train service. Now, when people hear the phrase Big Bang, the first image that often comes to mind is an explosion. A bright point detonates somewhere in darkness, throwing matter outward into empty space. It is an understandable picture. The name itself invites it. Big Bang sounds noisy. It sounds sudden. It sounds like something that would make the neighbours complain. But this picture, useful as a first impression, is not really what cosmologists mean. The Big Bang was not an explosion in space. It was an expansion of space. That difference matters. An explosion has a centre. It sends fragments outward into surroundings that already exist. But the Big Bang was not matter flying into a pre-existing emptiness. It was the early universe itself growing, cooling, and changing everywhere at once. There was no outside room into which it expanded, at least not in any ordinary sense. There was no edge where the universe ended and empty darkness began. The event was not located at one place far away. It happened everywhere, because everywhere we know was part of it. That can feel strange because our minds are trained by everyday experience. If something expands, we imagine it expanding into something else. Bread dough rises inside an oven. A balloon grows into the air around it. A crowd spreads into an open square. But with the universe, the idea is more subtle. Space is not simply a container that holds things. In modern cosmology, space is part of the thing that changes. The distances between faraway galaxies can grow because the fabric of space between them is stretching. When we look into deep space, we see that distant galaxies are moving away from us, and the farther away they are, the faster they appear to recede. That does not mean we are at the centre of the universe, any more than one raisin in rising dough is the centre of the loaf. From each raisin, the other raisins appear to move away. The whole dough is expanding. In the same broad way, every observer in the universe would see distant galaxies receding. The expansion is not pointing away from one privileged location. It is woven into the geometry of space itself. So when we ask what happened during the Big Bang, we are really asking what the universe was like when we follow cosmic history backward. Today, the universe is vast and cold by human standards. Galaxies are separated by enormous distances. Stars shine in islands of darkness. Radiation has stretched into a faint background glow. Matter has gathered into clumps, from galaxy clusters down to planets and pebbles, and people trying to remember where they left their glasses. But if we rewind the story, not with a machine but with observation and mathematics, the universe becomes denser. Galaxies were closer together. Radiation was hotter. Matter was packed more tightly. Go back far enough and the familiar structures disappear. There are no planets, no stars, no atoms. Even the ingredients of atoms cannot remain comfortably assembled. The universe becomes a hot, dense, rapidly changing sea of energy and particles, with conditions far beyond daily experience. The phrase "beginning of the universe" is also more delicate than it first appears. It is tempting to picture a first moment, like the opening page of a book. But physics becomes uncertain when we try to describe the very earliest instant. Our best tested theories can take us very far back, astonishingly far, to moments when the universe was unimaginably young. But there is a boundary where the known laws of physics stop being enough. Gravity, quantum behavior, extreme density, and the structure of space and time all meet there, and we do not yet have a complete theory that can describe them together with full confidence. So a careful scientist does not say that we know exactly what happened at the absolute first moment. Instead, we say that the universe was once in a hot, dense state, and that it has been expanding and cooling ever since. The Big Bang model describes this evolution remarkably well. It tells us how the early universe changed, how light elements formed, how the first free light was released, and how tiny early differences eventually grew into galaxies. But when we ask what came before, or whether before even has a sensible meaning, we are stepping into territory where honest curiosity must walk more slowly. This is one reason the Big Bang is not simply a story about the past. It is a story about the limits of knowledge. It asks us to hold two ideas at once. On one hand, we know a great deal. We have evidence written across the sky. We can measure the expansion of the universe. We can detect a faint afterglow from when the cosmos first became transparent. We can calculate the early formation of hydrogen and helium and compare those predictions with what we observe. We can map tiny temperature variations in ancient light, variations so small yet so important that they became the seeds of cosmic structure. On the other hand, the closer we push toward the beginning, the more mysterious things become. The universe does not hand us a simple photograph of its first instant. It offers traces, relics, patterns, and whispers. Cosmology is the art of reading those whispers without pretending they are louder than they are. It is worth taking a moment to imagine just how different the early universe was. Today, if you look up at night from a dark place, you see separation. There is space between stars. There is darkness between galaxies. There is quiet, at least from a human point of view. But in the very early universe, there was no night sky. There was no sky in the familiar sense. There were no stars to puncture the darkness because there was not yet darkness as we know it. Everything was filled with intense radiation. The cosmos was hot everywhere. It was not a place you could stand and look around, partly because standing requires atoms, solid ground, chemistry, and a fairly forgiving temperature, all of which were unavailable at the time. It was not hostile in the way a volcano or desert is hostile. It was more basic than hostility. It was a condition before the ordinary categories of environment existed. The universe also changed incredibly quickly at first. In our daily lives, big changes usually take time. Mountains rise slowly. Continents drift with almost comic patience. Even waiting for a kettle can feel like a small geological era. But the young universe evolved through major stages in tiny fractions of a second. Forces that are distinct today may once have behaved as a more unified whole. Particles appeared, interacted, vanished, and transformed in a blazing balance of energy. Space may have undergone a period of fantastically rapid expansion called cosmic inflation, a brief but powerful stretching that could help explain why the universe looks so smooth on large scales, while still containing the tiny irregularities needed to build galaxies. Then, as the universe expanded, it cooled. Cooling is one of the great themes of this story. Expansion allowed energy to spread out, and as the cosmic temperature fell, new kinds of structure became possible. The universe did not become interesting all at once. It became interesting because cooling opened doors. First came conditions where fundamental particles could exist in more stable ways. Then came a time when protons and neutrons could form. Later, some of those protons and neutrons joined into the nuclei of light elements. Not atoms yet, because the universe was still too hot for electrons to settle around nuclei without being knocked away. For a long period, the universe was a glowing plasma, a hot fog of charged particles and radiation. Light could not travel freely through it because it kept scattering from the charged particles around it. The cosmos was bright, but not transparent. Then, hundreds of thousands of years after the earliest hot dense state, the universe cooled enough for electrons to join with nuclei and form neutral atoms. That changed everything for light. Suddenly the fog lifted. Photons could travel across space without constantly being interrupted. Those photons are still travelling today, stretched by the expansion of the universe into the faint microwave glow we call the cosmic microwave background. It is one of the most important pieces of evidence we have, a kind of baby picture of the observable universe, though admittedly not the sort anyone would keep in a family album unless the family was made entirely of radio telescopes. After that, the universe entered a long dim period. Atoms existed, but stars had not yet formed. Gravity slowly gathered matter into denser regions. The tiny unevenness left from the early universe became increasingly important. Where matter was slightly denser, gravity pulled in more matter. Over time, clouds collapsed, heated, and eventually ignited the first stars. Those stars changed the universe again. They produced heavier elements in their cores and scattered them through space when some of them died. Later generations of stars and planets formed from enriched material. Carbon, oxygen, iron, and many other elements were forged in stellar processes long after the Big Bang itself. This is an important distinction. The Big Bang made the early light elements in large amounts, especially hydrogen and helium, with small traces of others. It did not directly make the full chemical richness of the world around us. The gold in jewellery, the calcium in bones, the oxygen we breathe, and the iron in blood belong to a longer cosmic history involving stars. The Big Bang prepared the stage and the simplest ingredients. The stars did much of the later cooking. In a universe this old, even dinner has ancestry. So tonight, as we move into this story, we will not treat the Big Bang as a single flash, and then move on. We will slow it down, not because the event itself was slow, but because understanding it requires patience. We will begin near the edge of what physics can describe and carefully step forward. We will ask whether there was a before, and what that question might mean if time itself is part of the universe. We will look at the first tiny fraction of a second, when reality was too extreme for ordinary intuition. We will explore inflation, the strange burst of expansion that may have shaped the universe on enormous scales. We will follow the appearance of particles, nuclei, atoms, light, darkness, stars, and the evidence still reaching us from that early age. Along the way, we will gently separate what scientists are confident about from what remains speculative, because the universe is quite mysterious enough without adding unnecessary fog. There is something calming, I think, about learning the Big Bang properly. At first, it seems overwhelming. Everything began hot, dense, and rapidly expanding. Space stretched, matter formed, light was trapped, then released. Stars came later, galaxies gathered, billions of years passed. Eventually, on one small planet around one ordinary star, life became complicated enough to wonder where it came from. That is a lot for a sleepy mind to carry. But when you let the story unfold in order, it becomes less like a sudden blast and more like a long transformation. The universe did not simply appear as it is now. It cooled into possibility. It changed from a state where atoms could not exist into one where chemistry could happen. Then stars, then planets, then oceans, then nervous systems, then questions spoken softly at night. And perhaps that is why this subject feels so strangely personal, despite its enormous scale. The Big Bang is not just something that happened far away and long ago. It happened here, in the sense that every region of space around us was once part of that early hot, dense universe. The place where your room is now, the air between you and the wall, the space around the moon, the space between galaxies, all of it shares that history. We are not looking at the beginning from the outside, we are inside its aftermath. Every second, the universe continues to expand. Every night skies a later page in the same cosmic story. Every atom of hydrogen in your body has roots reaching back to the earliest minutes of cosmic history. That does not mean you need to feel grand or important in some dramatic way. It may be enough simply to feel connected, quietly and physically, to the deep past. So settle in. Let the day step back a little. Let the ordinary measurements of time soften around the edges. The beginning of everything is not a simple place to visit, but we can approach it carefully with good evidence, clear language, and perhaps the occasional forgiving joke when the universe becomes too large for the human brain to hold all at once. We will start not with a bang in empty space, but with a universe that was once hotter, denser, smoother, and younger than anything we can picture directly. We will follow it as it expands and cools, as the first possibilities appear, as light waits for its chance to travel freely, and as the seeds of all later structure begin to take shape. For now, just notice the quiet fact that you are here, listening from some small location in a vast, expanding cosmos, asking how it all began. That question has carried human curiosity from myth to mathematics, from campfires to space telescopes, from simple wonder to careful measurement. And somewhere behind it all is the early universe itself, not exploding into space, but becoming the space in which every future thing would one day happen. To ask what happened before the Big Bang is one of those questions that seems simple until you sit with it for a moment. It sounds like asking what happened before breakfast, or before a storm, or before someone knocked on the door. We're used to things having earlier things behind them. A seed comes before a tree. A cloud comes before rain. A sleepy decision to check one more message comes before suddenly discovering that an hour has vanished. Our minds like sequences. They like one event lined up behind another, each cause leaning gently on the one before it. So when we hear that the universe began in a hot, dense state, it is completely natural to ask what came before that. Was there darkness waiting patiently? Was there empty space, silent and unused? Was there some earlier universe that collapsed, bounced, and became ours? Or was there, in the strictest and strangest sense, no before at all? This is where the question becomes delicate. In everyday language, before is a time word. It only makes sense when time is already available. To ask what happened before a birthday is easy because the calendar exists on both sides of the event. To ask what happened before sunrise is easy because the night was already unfolding. But if time itself is tied to the universe, if time is not just a background clock outside reality, but part of the physical structure of reality, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The words feel meaningful at first, but when you examine them carefully, they may be pointing beyond the map where their usual meaning stops working. That does not mean the question is foolish. It means the question is deep enough that we have to be careful with the language we use. For a long time, the simplest popular answer was that the Big Bang was the beginning of everything. Space began, time began, matter and energy began. There was no earlier moment because moments themselves belong to the universe. In this view, the Big Bang is not an event that happened inside time. It is the boundary from which time, as we understand it, starts to unfold. That idea can be hard to picture because picturing already puts us outside the scene, as though we are standing in some quiet viewing room watching the universe appear. But there may be no outside viewing room. There may be no external clock. There may be no empty stage waiting for the first actor to arrive. The stage, the clock, the actors, the lighting, and the suspiciously expensive theatre snacks are all part of the same cosmic production. When scientists trace the expansion of the universe backward, they find that the observable universe was once hotter, denser, and more uniform. Galaxies were not yet galaxies. Stars were not yet stars. Atoms were not yet atoms. Keep rewinding, and the density and temperature rise toward conditions where our familiar theories become strained. General relativity, Einstein's theory of gravity, is excellent at describing large-scale space and time. Quantum physics is excellent at describing the small and uncertain world of particles and fields. But the earliest universe asks both theories to work together under extreme conditions, and that is where the trouble begins. At the very beginning, if we push the known equations too far, they suggest something called a singularity, a state where density and temperature become infinite and ordinary physics breaks down. But most physicists do not treat that infinity as a real, physical object sitting at the start of history. They treat it as a warning sign. It is the universe's way of saying, in rather firm handwriting, that our current theory has been carried beyond the place where it can safely go. A singularity is not so much an answer as a signpost pointing toward missing physics. It tells us that the early universe was incredibly extreme, but it does not tell us exactly what happened at the absolute first moment. It is a little like using a map that works beautifully across the whole countryside, then finding that when you reach the edge of a cliff, the path continues straight into the air. The map is not useless. It brought you a long way. But right at the edge, you need better information. In cosmology, that better information would likely come from a theory of quantum gravity, a deeper framework that explains how gravity behaves when the universe is tiny, dense, and quantum effects cannot be ignored. We do not yet have a fully confirmed theory of that kind. We have ideas, some elegant, some strange, some mathematically powerful, some still waiting for evidence. This is why honest discussions of the earliest beginning always include a careful pause. One possibility is that time truly begins with the Big Bang. Not time as measured by clocks, because clocks did not exist, but time as an aspect of the universe. In this picture, there is no earlier state in the ordinary sense. The question of before has no physical answer, because there was no time in which an earlier condition could exist. This can feel unsatisfying, because the human mind tends to reach behind every curtain. If we are told there was no before, we may immediately wonder what was sitting there being no before, which is exactly the sort of sentence that makes cosmology both fascinating and mildly unfair. But the idea is not simply wordplay. Relativity already taught us that time is not separate from the universe. Time can stretch and slow depending on motion and gravity. It is part of space-time, not a universal metronome ticking beyond all things. So the thought that time might have a beginning is strange, but it is not absurd. There is another way to soften the idea. Think about the surface of Earth. You can travel north from many places. You can go farther north and farther north until you reach the North Pole. Once you're there, asking which direction is farther north no longer works. The surface itself has not ended in a wall. You have not fallen off reality. It is simply that the coordinate north has reached its limit. Some cosmological models suggest something similar for time near the beginning. The universe may be finite in age without needing a moment before it, just as Earth's surface is finite in size without needing an edge where the ground suddenly stops. The comparison is not perfect, of course, because space and time are not the same as walking across snow in a large coat, but it helps loosen the grip of the assumption that every beginning must have a normal earlier scene behind it. Another possibility is that the Big Bang was not the absolute beginning, but a transition. Perhaps our expanding universe emerged from an earlier phase. Some models suggest a cosmic bounce. In these ideas, the universe may have been contracting before it began expanding. Instead of starting from an infinite singularity, the cosmos reached a very small, dense state, and then rebounded. This can be appealing because it replaces the sharp beginning with a kind of bridge from one cosmic era to another. A previous universe collapses, conditions become extreme, quantum effects prevent complete collapse, and expansion begins again. It is a dramatic picture, though not dramatic in the noisy fireball sense. More like the universe inhaling and exhaling on a scale that makes lungs seem very underqualified. But bounce models face difficult questions. What exactly caused the bounce? How did the previous contracting phase avoid becoming a singularity? What evidence would remain in our present universe? If there was an earlier cosmic era, could any information from it survive the violence and density of the transition? Some versions predict subtle patterns that might one day be detected in the cosmic microwave background or in the distribution of matter across space. Others remain extremely hard to test. That does not make them useless. Speculative ideas can guide new mathematics and new observations, but in science, a beautiful possibility must eventually meet evidence. The universe is under no obligation to be as elegant as our favourite notebooks. There are also ideas involving inflation, the proposed period of extremely rapid expansion in the very early universe. Inflation was introduced to explain several puzzling features of the cosmos, including why the universe looks so smooth on very large scales, and why space appears so close to geometrically flat across the observable region. In many versions, inflation begins from a high-energy state and stretches space at an astonishing rate. But inflation also raises the question of what came before inflation. Did inflation start at the Big Bang? Did something set it off? Was it eternal into the past? Or did it also require a beginning? Some models of eternal inflation suggest that inflation may continue forever in some regions, producing many bubble universes like ours. In such a picture, our Big Bang could be the local beginning of our observable region, not the absolute beginning of all reality. Somewhere beyond what we can observe, other regions might have formed, each with its own history, perhaps even different physical properties. This idea is fascinating, but it is also difficult to test directly. If other bubble universes exist beyond our cosmic horizon, their light may never reach us. They would be outside the observable universe, not merely far away in the ordinary sense, but separated from us by the way space-time itself has expanded. Cosmologists can look for indirect signs, such as possible imprints from collisions between bubble regions, but no confirmed evidence has been found. So the multiverse remains an interesting possibility rather than an established fact. It is the kind of idea that invites both excitement and caution. Excitement, because it expands our imagination of what reality could be. Caution, because imagination alone, even when wearing a lab coat, is not the same as measurement. Another approach comes from quantum cosmology. In some proposals, the universe does not begin from a classical point in time, but from a quantum condition where ordinary time is not yet defined in the usual way. One famous idea is sometimes called the no-boundary proposal. In simple terms, it suggests that the early universe may be rounded off rather than sharply beginning. Time near the beginning behaves somewhat like a spatial direction, so there is no hard edge, no first instant in the ordinary sense, and no need for a before. The universe can be finite in the past without having a boundary, where one must ask what happened earlier. This is difficult to visualize, and anyone who claims it is easy may also be trying to sell you a very complicated toaster. But the basic goal is clear. It tries to remove the singularity and replace it with a smoother quantum origin. There are also ideas in which the universe begins through a quantum fluctuation. This phrase is often misunderstood. People sometimes say the universe came from nothing, but nothing in physics often does not mean absolute philosophical nothing. A quantum vacuum is not empty in the simple sense. It has fields, laws, structure, and the potential for activity. It is not a blank absence. It is more like the quietest possible room in a house that still has wiring in the walls, air in the corners, and a cat probably hiding under something. When physicists discuss quantum creation, they're usually talking about a state described by physical laws, not a magical appearance from total non-being. The deeper question, why there are laws or fields at all, may lie beyond physics, or at least beyond its current tools. Science can describe how one physical state may lead to another. Asking why there is something rather than nothing may be a larger philosophical question, though cosmology certainly gets close enough to knock politely on its door. So was there anything before the Big Bang? The most careful answer is that we do not yet know, and the meaning of before may itself depend on the correct theory of the earliest universe. There may have been no before because time began with the hot, dense origin of our universe. There may have been a previous contracting phase. There may have been an inflationary background from which our region emerged. There may be a quantum description in which the beginning is not a sharp moment but a smooth, boundaryless condition. There may be possibilities we have not yet imagined because our brains evolved to deal with fruit, weather, social awkwardness, and remembering where the path home is, not with the birth of spacetime. That is not an insult to the brain. It has done very well, considering its original job description did not include reconstructing the first moments of the cosmos. What we can say with much more confidence is that the Big Bang model does not require an explosion into pre-existing space. It describes the expansion and cooling of the universe from an early hot dense state. It explains why distant galaxies recede, why the universe contains the light elements in the proportions we observe, and why a faint background glow fills the sky in every direction. These are not guesses made because the story sounds nice. They are evidence-based pillars. The uncertainty lies not in whether the universe was once hotter and denser. The uncertainty lies in what happened at the deepest edge of that description, where known physics becomes incomplete. That distinction matters. It is the difference between saying we know nothing and saying we know a great deal, but not everything. The second is less dramatic, but it is much more accurate, and in science, accuracy is a form of respect. There is a calming honesty in that. The beginning of the universe is not a solved riddle with a neat card tucked under the table. It is an active frontier. Telescopes, particle experiments, gravitational wave observatories, and mathematical theories all contribute pieces of the puzzle. The cosmic microwave background gives us a view of the universe when it was hundreds of thousands of years old, which is ancient by human standards but infancy by cosmic standards. The abundances of hydrogen, helium, and other light elements take us back to the first minutes. Particle physics helps us understand conditions at tiny fractions of a second. But the absolute beginning, if that phrase is even correct, remains partly hidden. Not hidden because the universe is being secretive in a personal way, of course. The universe is not refusing to answer. It is simply written in a language we are still learning to read. The question also changes how we think about emptiness. Before learning cosmology, it is easy to imagine nothing as a dark, empty room. But a dark, empty room is still a room. It has space. It has time. It has dimensions. It has the possibility of placing a chair in it, even if the chair would make the room look slightly less mysterious. True nothing, if such a concept is physically meaningful, would not be darkness or silence. Because darkness is what you get when light is absent inside space, and silence is what you get when sound is absent inside time. A universe with no space and no time is not an empty stage. It is the absence of the stage itself. That is why the question before the bang is so hard. We keep trying to imagine a dark waiting area before the universe begins, but but the waiting area already smuggles in space and time. It is very difficult to remove those from the imagination because imagination itself seems to arrange thoughts in a kind of inner space and sequence. Still, human beings have always wondered about origins. Long before modern cosmology, cultures told stories about beginnings. Some began with waters, some with darkness, some with a cosmic egg, some with a word, some with a separation of earth and sky. These stories were not physics in the modern sense, but they reveal something constant about us. We want to understand why there is a world at all. Modern science approaches the question differently. It does not begin with meaning, but with measurement. It asks what observations can be made, what predictions follow, what models survive comparison with the sky. Yet even in its careful form, cosmology touches the same old human wonder. We are still looking up, still asking where all this came from. Only now we have radio telescopes, satellites, particle accelerators, and computers doing calculations that would make an ancient storyteller either impressed or very keen to go back to bed. There is also a personal side to this. When you ask what came before the Big Bang, you are not only asking about distant physics, you're asking about the beginning of the conditions that made your own existence possible. If the early universe had expanded differently, if matter had not formed in the right way, if tiny irregularities had not grown under gravity, if stars had never ignited, then there would be no planets, no chemistry rich enough for life, no one lying awake wondering whether time began or whether the universe bounced. The question reaches from the larger scale to the most intimate. It connects the mystery of space-time to the simple fact that you are here, breathing, listening, perhaps getting a little sleepy, which is an entirely reasonable response to contemplating quantum gravity. As we approach the first tiny fraction of a second, it helps to carry this uncertainty gently rather than treat it as a problem to be hurried past. The lack of a final answer about before does not weaken the story. It gives it depth. The known universe has a history we can trace with remarkable success, but the earliest boundary of that history remains one of the great open questions. Maybe time began there, maybe time changed character there. Maybe our universe emerged from something earlier that we do not yet know how to describe. Each possibility asks us to stretch our thinking, but not to abandon evidence. That balance is where the real beauty of cosmology lives. It invites imagination, then asks imagination to sit beside observation and behave itself. So for now, we can say this. Before the Big Bang may not have been a place, a darkness, or an empty silence. It may have been no time at all, or a quantum state unlike anything in daily life, or an earlier cosmic phase hidden behind the hot, dense beginning we can describe. The honest answer is not a single dramatic sentence, but a careful doorway. On this side of it, the universe expands and cools, leaving evidence across the sky. Beyond it, our theories are still reaching. And as they reach, they bring us closer to the first moments we can speak about with increasing confidence, when the universe was not yet filled with stars or atoms or even stable matter as we know it, but was already beginning the transformation that would lead, after an almost unbelievable span of time, to galaxies, planets, and quiet minds asking what came before. By the time we reach the first tiny fraction of a second, we have already stepped beyond the comfortable habits of ordinary thinking. We are no longer imagining the universe as a dark room waiting for matter to arrive, and we are no longer picturing an explosion throwing fragments into empty space. The picture is stranger and more precise than that. The early universe was space itself in an extremely hot, extremely dense state, changing so quickly that our usual sense of before and after begins to feel far too slow. A second is a small amount of time in daily life. It is one tick of a clock, one blink, one small pause before answering a question. But in the early universe, a second was enormous. Vast amounts of physical change happened in intervals so short that writing them out with ordinary numbers would make the page look as though a very nervous accountant had been trapped in a physics department. So let us approach it gently. Not because the universe was gentle then, it certainly was not, but because our minds need a little kindness when dealing with conditions this extreme. The first tiny fraction of a second was not filled with stars, atoms, or even stable particles in the way we usually imagine them. It was a state of energy and fields, of rapid interactions, of heat so intense that matter could not yet settle into familiar forms. The universe was not empty, and then suddenly full. It was full from the beginning of the part we can describe, but what it was full of changed as it expanded and cooled. This cooling did not mean the universe became cold, it only means that it became less impossibly hot than it had been just a moment earlier. In the early cosmos, less impossibly hot can still mean conditions far beyond the centre of any star. The earliest moment that physics can speak about with even partial seriousness is often described as the limit where our current understanding becomes uncertain. We can follow the universe back to an incredibly young age, but at the very edge, gravity and quantum physics must both matter strongly. General relativity tells us how space and time behave under gravity. Quantum physics tells us how matter and energy behave at tiny scales. But the first instance need both stories at once. That is difficult because these two great theories, both enormously successful in their own territories, do not yet merge into one fully tested description. It is a little like having two excellent maps, one for the mountains and one for the sea, and discovering that the place you need to cross is somehow both storm and cliff at the same time. The maps are not wrong. They are just incomplete for this particular landscape. Because of that, scientists are careful about the absolute beginning. We should not pretend to know exactly what happened at the first instant. The universe may have passed through a state where the very ideas of space and time were not yet behaving as they do now. Distances may not have meant what distances mean today. Time may not have flowed in the familiar way. Even saying that something happened during that earliest limit can be tricky, because happened is a word that assumes time is already acting like a sequence. Still, just after that unknown boundary, our models become more useful. The universe can be described as intensely hot, dense, and expanding. From there, physics begins to give us a story with more structure. Imagine, very carefully, not a place but a condition. Everywhere is packed with energy. There are no solid objects, no empty gaps between stars, no calm background darkness. Space is not filled with things in the usual way because the things themselves are not yet familiar. What exists are quantum fields, the underlying physical fields from which particles can appear. In modern physics, particles are not usually treated as tiny hard beads that simply sit in space. They are excitations of fields, little disturbances that behave like particles when observed in particular ways. In the very early universe, these fields were in an incredibly energetic state. Interactions happened constantly. Particles and antiparticles could appear and disappear. Energy shifted form. Nothing had time to become ordinary. At such high temperatures, distinctions that seem basic today may not have been present in the same way. In the world around us, nature has different fundamental forces. Gravity pulls matter together across vast distances. Electromagnetism governs light, electricity, magnetism, and chemistry. The strong nuclear force holds atomic nuclei together. The weak nuclear force participates in certain kinds of particle changes and radioactive processes. Today, these forces behave differently. They have different strengths, different ranges, and different roles. But in the early universe, when temperatures were far higher, some of these forces may have been unified, acting as different aspects of a deeper shared interaction. As the universe cooled, that unity may have broken into the separate forces we see today. This idea is called symmetry breaking, and although the phrase sounds technical, the basic idea can be understood through a simple comparison. Think of water cooling into ice. Liquid water is free to move in many directions. It has a kind of smoothness. But when it freezes, molecules settle into a more specific pattern. The underlying substance is the same, but the state has changed, and with that change come new properties. The early universe may have gone through transitions something like this. though far more extreme and involving fields rather than water. At very high energy, the universe may have been more symmetric, with certain differences hidden. As it cooled, the field settled into particular states, and the forces of nature took on their distinct identities. It was not a choice or a decision. It was physics finding its lower energy arrangement as the cosmos expanded. One of the most important fields in this story is associated with the origin of mass for many particles. Today, particles such as electrons and quarks have mass, and that mass plays a key role in allowing matter to form atoms, stars, and bodies. In the early hot universe, the field connected with this process would have behaved differently than it does now. As the universe cooled, it settled into the state we observe today, giving many particles the masses that allow the later universe to work as it does. Without that transition, the story of matter would be completely different. Particles might not combine in the same way, atoms might never form, chemistry might be impossible. The quiet cup beside your bed, if you have one, depends on deep physical processes that took shape when the universe was younger than any ordinary clock could meaningfully measure. During these tiny fractions of a second, the universe was also filled with pairs of matter and antimatter. Antimatter is not science fiction decoration, though science fiction has certainly enjoyed it. For many types of matter particles, there are corresponding antimatter particles with opposite properties. When matter and antimatter meet, they can destroy each other and turn into energy. In the early universe, energy was so abundant that matter and antimatter were constantly produced. You might expect that equal amounts of each would have formed, and if that had been perfectly true, nearly all matter and antimatter would have vanished together, leaving behind mostly radiation and very little material for stars, planets, or anyone to ask inconvenient questions late at night. But that is not what happened. Our universe contains matter. Antimatter exists, but it is rare compared with matter in the observable cosmos. This means that in the early universe, there must have been a tiny imbalance. For every great number of matter and antimatter particles that destroyed each other, a small excess of matter remained. That tiny leftover became the material universe. Galaxies, stars, planets, oceans, and living cells are made from the residue of a slight early preference for matter over antimatter. This is one of the most important unsolved problems in cosmology and particle physics. We know that such an imbalance must have occurred because we are here. We have ideas about how it might have happened, involving processes that treat matter and antimatter slightly differently, but the full answer is still being studied. It is humbling to realize that everything solid and familiar may exist, because the early universe was not perfectly even-handed. As the universe continued to expand, the temperature dropped enough for certain particles to become stable for longer. Quarks, which are among the building blocks of protons and neutrons, existed in a hot, dense mixture along with gluons, the particles associated with the strong nuclear force. This state is often called a quark-gluon plasma. It was not a plasma like the glowing gas in a neon sign, though that is a useful everyday word for some kinds of ionized matter. This was much more extreme. Quarks were not yet locked inside protons and neutrons as they are today. They moved in a dense energetic sea, interacting constantly. The universe at this point was still so hot that ordinary nuclei could not exist. Even the pieces that would later become nuclei were not yet assembled in the familiar way. Then, as expansion continued, the temperature fell further. Quarks became confined into composite particles, including protons and neutrons. This was a major step toward the later formation of atoms, though atoms themselves were still far in the future. A proton is not an atom. A neutron is not an atom. Even a nucleus is not an atom. To get atoms, electrons must later settle around nuclei, and the universe would remain too hot for that for a very long time. But the formation of protons and neutrons mattered enormously. These particles would later participate in the creation of the light atomic nuclei, especially hydrogen and helium. The material foundation of the visible universe was beginning to take shape, though still in a form far too hot and energetic for any chemistry. It is easy to underestimate how crowded the early universe was. Today, space feels mostly empty. Even inside matter, atoms are mostly space, and between stars the distances are enormous. But in the first tiny fractions of a second, density was immense. Particles were packed together, radiation was everywhere, collisions were constant. The universe was not like a collection of objects sitting in a room. It was more like an all-surrounding energetic medium where every region was part of the same rapidly evolving state. If there had been a way to place a tiny observer there, which there was not because observers require stable matter, atoms, chemistry and other luxuries the universe had not yet arranged, that observer would not have seen a night sky or a landscape. There would have been no direction to point where the beginning was happening. It was happening everywhere. This point is worth resting on for a moment. The early universe was not small in the sense of being a little ball located somewhere. The part of the universe that would become our observable region was once compressed into a much smaller volume, but the whole universe may have been infinite even then. If the universe is infinite now, it may have been infinite at the beginning as well, just with every distance scaled down and every region much hotter and denser. Infinite things can expand in the sense that the distances between points grow. That is not easy to picture because our brains prefer objects with edges. But the Big Bang was not the expansion of an object into surrounding emptiness. It was the expansion of space, whether that space was finite or infinite. The first tiny fraction of a second happened throughout the whole universe, not at a central spark. Another important feature of this early period is that tiny quantum fluctuations may have been present. Quantum physics tells us that fields cannot be perfectly still in the simple classical sense. There are always small variations. In the early universe, these variations were microscopic, but they mattered. Later, during the rapid stretching associated with inflation, they may have been magnified to cosmic scales, becoming the seeds of the structure we observe today. This is where the story begins to connect the extremely small with the extremely large. A tiny fluctuation in an early field could eventually correspond to a slightly denser region of the universe. Over vast amounts of time, gravity would act on those slight differences, pulling matter into clouds, then stars, then galaxies. The largest structures in the cosmos may trace their ancestry to quantum uncertainty in the first moments. That is not poetic exaggeration. It is one of the central ideas linking early universe physics to the maps of galaxies and ancient light we study today. Still, before we move fully into inflation, it helps to notice how much had to be arranged by physical law in that first fraction of a second. The universe needed to expand at a rate that allowed structure, but did not collapse immediately, or spread matter too thin too quickly. It needed tiny irregularities, but not huge ones. Too smooth, and perhaps no galaxies form. Too uneven, and the universe becomes a very different place. It needed matter to survive over antimatter by a tiny margin. It needed fields to settle into states that allowed particles to have the properties we observe. It needed the forces of nature to take the forms that later made nuclei, atoms, chemistry, and stars possible. None of this should be imagined as someone tuning knobs on a machine. It is simply what the physical history of our universe appears to have done. But when laid out step by step, the early universe begins to seem less like a single moment, and more like a rapid sequence of transitions, each one opening the door to the next. The word temperature also deserves careful handling here. When we say the early universe was hot, we're not talking about heat in the ordinary household sense. A hot oven is hot because the atoms and molecules inside it are moving energetically, and because radiation is present. But in the earliest universe, atoms did not exist. The temperature refers to the average energy of the particles and radiation in that dense state. It is a measure of how energetic the whole system was. As the universe expanded, the wavelengths of radiation stretched and the average energy decreased. This is the same broad process that, much later, stretched the ancient light of the cosmic microwave background until it became a faint microwave glow. Expansion and cooling are tied together throughout cosmic history. The universe does not cool because it is losing heat into some outside space. There is no outside refrigerator. It cools because space itself expands, spreading energy across increasing distances. During the first tiny fraction of a second, cause and effect also behave within a universe whose regions could not all communicate with each other in the ordinary way. Light travels fast, but not infinitely fast. In a very young universe, there has been very little time for signals to move from one region to another. This creates a puzzle. When we observe the cosmic microwave background today, we find that widely separated regions of the early universe had almost the same temperature. Yet without some special explanation, those regions should not have had time to exchange information and come into balance. This is one of the reasons inflation became such an important idea. If a small region had once been in causal contact, meaning its parts could influence one another, and then that region was stretched enormously, it could explain why the visible universe appears so uniform across vast distances. The details of that stretching belong to where we are heading next, but the problem it solves is already visible in these first moments. There is a temptation, when speaking about the early universe, to make everything sound settled and complete. It is more honest to say that some parts are strongly supported, while others remain active research. The hot, dense early state is well supported. The expansion of the universe is well supported. The later formation of light elements is well supported. The cosmic microwave background is a powerful piece of evidence, but the physics of the very earliest fraction of a second is harder to confirm directly. We cannot build a laboratory universe and rerun the beginning, which is probably for the best, since most safety committees would have concerns. Instead, scientists use a combination of particle experiments, astronomical observations, and mathematical models. They look for traces. They ask what each early process would leave behind. A theory about the first fraction of a second becomes stronger if it explains what we already observe and predicts something new that can be tested. This is why the earliest universe is not just a subject for imagination. It is tied to real measurements. Particle accelerators recreate tiny pieces of high-energy physics, though not the full conditions of the beginning. Telescopes map the distribution of galaxies, searching for patterns that reveal how structure grew. Observations of the cosmic microwave background measure ancient temperature variations with extraordinary precision. Future gravitational wave detectors may one day reveal signals from extremely early cosmic events, perhaps even from transitions that happened when the universe was far younger than the moment represented by the cosmic microwave background. Gravitational waves are ripples in space-time itself, and unlike light, they may carry information from times when the universe was opaque to radiation. If we could detect a background of primordial gravitational waves, it might offer a new way to listen to the first fraction of a second. Not with ears, of course. With instruments so sensitive they make the idea of listening seem almost too casual. The first tiny fraction of a second also forces us to rethink what an origin story can be. In ordinary stories, beginnings are often simple. A person is born, a journey starts, a door opens. But the beginning of the universe, or at least the earliest describable part, is not simple in that way. It is a chain of physical conditions, some known, some uncertain, unfolding rapidly as space expands. There is no scenery. There are no objects, there is no observer, there is no sound despite the name Big Bang, because sound requires a medium and a listener, and the early universe was not making a noise in empty air. The name is catchy, but misleading. What actually happened was not a bang in the ordinary sense. It was a transformation of the entire cosmos from a hotter, denser condition into a cooler, more structured one. The earliest fraction of a second was the beginning of that transformation becoming physically distinct. If you are listening in a quiet room now, this may seem almost impossibly remote. The early universe was hot enough to prevent atoms from existing, while your room is full of stable matter. The early universe was dense and uniform, while your world is full of separated objects. The early universe changed dramatically in tiny intervals, while the clock near you may be moving with almost rude calmness, yet the connection is direct. The protons in the atoms of your body trace back to those early processes. Many of them have survived for nearly the entire age of the universe. The hydrogen that later became part of water, organic molecules, stars and worlds began its long history in the aftermath of these first events. You are not merely made of star stuff. Though that is true for many of the heavier elements, you're also made partly of Big Bang stuff, the simpler ingredients that formed before any star had ever shone. As the universe aged through that first tiny fraction of a second, it became less unified, less extreme, and more capable of forming structure. That may sound backward, because we often think of complexity as something that comes from adding energy. But in the cosmic story, cooling is creative. When things are too hot, structures are torn apart as quickly as they form. Lower the temperature, and new arrangements become possible. Quarks can bind into protons and neutrons. Later, nuclei can form. Much later, atoms can exist. Later still, molecules can assemble, gas can cool, stars can ignite, planets can form, and chemistry can become elaborate enough to make sleep difficult when the mind starts asking cosmological questions at midnight. The first fraction of a second did not contain all those later structures, but it made their future possible by setting the physical conditions from which they would emerge. The universe at this stage was also expanding everywhere, and that expansion was not simply a background detail. It controlled the pace of cooling. It affected which particles could remain common and which would vanish. It influenced the balance between interactions. When the universe was extremely hot, particles interacted rapidly enough to remain in thermal balance, constantly exchanging energy. As expansion continued, some interactions could no longer keep up. Certain particles effectively decoupled from the rest, meaning they stopped interacting often enough to stay in equilibrium with the surrounding cosmic mixture. This idea of decoupling will become very important later when light itself finally travels freely, but the pattern begins early. The expanding universe gradually separates processes that were once tightly linked. It is remarkable that so much of this story can be inferred at all. No one watched the first fraction of a second. There were no witnesses, no fossils in the ordinary sense, no little plaque saying the universe became interesting here. Yet the present universe carries evidence of its youth. Its expansion tells us it was once denser. Its background radiation tells us it was once hot and opaque. Its light element abundances tell us nuclear reactions happened in the early minutes. Its large-scale structure tells us small early variations grew under gravity. The first fraction of a second remains the hardest part, but it is not disconnected from observation. It is the upstream portion of a river whose later waters we can sample. We infer the source by studying the flow, the minerals, the banks, and the shape of the valley. Cosmology often works like that. It turns the sky into a record of processes too old and too vast to handle directly. There is a quiet lesson in this early period. The universe we know did not need familiar things in order to begin becoming familiar. It did not start with atoms and then build larger objects. It started in a state where atoms were impossible. It did not start with light moving freely through space. Light was trapped for a long time. It did not start with planets waiting in darkness. Planets required stars, and stars required gravity, matter, cooling, and time. The first fraction of a second belongs to a world before worlds, before chemistry, before surfaces, before any distinction between day and night. Yet it is not separate from us. It is the first stage of the physical continuity that leads here. And as that first tiny interval gives way to the next, one idea begins to take on special importance. The universe is already expanding and cooling, but to explain why it looks so smooth across enormous distances, why space appears so balanced, and how tiny quantum fluctuations could become the seeds of galaxies, cosmologists propose that there may have been a brief period of extraordinarily rapid stretching. Not an explosion, not matter rushing outward through emptiness, but space itself expanding with astonishing speed. This possibility, known as cosmic inflation, takes the already strange early universe and makes it stranger still, while also solving several problems that would otherwise remain deeply puzzling. So we move from the first moments of heat, fields, particles, and uncertainty toward the idea that the infant cosmos may have grown by an almost unimaginable amount in an almost unimaginably short time, setting the stage for the vast and surprisingly orderly universe we see around us now. By this point in the story, the universe has already become a very strange place to imagine, which is impressive considering it has barely had any time to be anything at all. We have followed it back to a state so hot and dense that ordinary matter could not yet exist, where the familiar forces of nature may not have fully separated into their present roles, and where tiny quantum variations may have been flickering in the background of reality. The early universe was expanding, cooling, and changing, but there is a puzzle waiting there, and it is not a small one. When scientists looked carefully at the universe we can observe today, they found that it is surprisingly smooth on the larger scales. In every direction, distant space looks broadly similar. The ancient glow left over from the early universe has almost the same temperature across the whole sky. Galaxies are not arranged in a perfectly even mist, of course. They gather in clusters, filaments, sheets, and great cosmic webs. But when you step back far enough, farther than any human journey could ever take us, the universe looks remarkably uniform. That uniformity is comforting at first. It makes the cosmos feel orderly, as though it had been carefully stirred before being placed in the oven. But for cosmologists, it created a serious problem. Regions of the early universe that now lie on opposite sides of the observable sky appear to have nearly the same temperature. Yet in the simplest version of the Big Bang picture, those regions should never have had time to exchange light, heat, or information. They were too far apart, too early, with too little time for signals to travel between them. So how did they end up so similar? It is a bit like walking into a very large house and finding that two rooms on opposite ends, with no shared heating system and no open doors between them, are exactly the same temperature down to a tiny fraction. You could say it was luck, but scientists are generally suspicious of luck when it appears everywhere at once and refuses to explain itself. This is called the horizon problem. The word horizon here does not mean the line where the sky meets the ground. It means the limit of what could have influenced what. Because light has a finite speed, and because the universe has a finite age, there are regions that could not have been in contact during the earliest ordinary expansion. Yet they look as though they once shared a common history. The cosmic microwave background that ancient light released when the universe became transparent much later shows tiny temperature differences, but the overall sameness is astonishing. The differences are real and important, but they are small. Without some additional process, the smoothness of the early universe seems difficult to understand. There was another puzzle too. The universe appears to be very close to geometrically flat on large scales. Flat here does not mean flat like a table or a sheet of paper floating in space. It refers to the geometry of space itself, to the way distances and angles behave across the cosmos. A universe with too much curvature would evolve differently. If the early universe had been even slightly different in its overall balance, that curvature could have grown more obvious over time. Yet today, observations show a universe that is very close to flat. In the older Big Bang picture, this required the early universe to have been set up with extraordinary precision. It was as though the cosmos had balanced a pencil on its tip and then kept it balanced for nearly 14 billion years, which is hard enough on a desk, let alone for all of space. This is called the flatness problem. It asks why the universe began with conditions so finely arranged that it still looks so close to flat today. A third issue came from certain particle theories, which suggested that the early universe might have produced strange heavy relics, objects or particles that should still be around in large numbers if the simplest early history were correct. But we do not observe them in the expected abundance. This is sometimes called the monopole problem, although the details depend on specific theories of high-energy physics. The important point for our quiet journey is that the early universe seemed to have been smoothed, flattened and cleaned of unwanted relics in a way the basic picture did not easily explain. Then came the idea of cosmic inflation. Inflation proposes that very early in the universe, for an extremely brief interval, space expanded at an enormous rate. This was not matter flying through space faster than light. That would violate the rules of relativity if we described objects moving locally through space. Inflation is different. It is the expansion of space itself. Distant regions can be carried apart by expanding space faster than light could travel between them, because the speed limit applies to motion through space, not to the stretching of space as a whole. This distinction is subtle but important. No galaxy, particle, or little cosmic pebble was zooming through its local neighbourhood faster than light. Instead, the distance between regions grew because the underlying space expanded. The idea sounds almost too dramatic. A tiny region of the early universe, once small enough to have been in thermal contact, could have stretched into a size vastly larger than the observable universe. If that happened, it would explain why distant regions look so similar. They were once close enough to exchange information and settle into nearly the same temperature. Then, inflation pulled them apart so quickly and so far that they now appear in opposite directions of the sky. The universe looks uniform because the patch we can see came from a once connected region that was stretched enormously. It is like taking a small, smooth piece of fabric and stretching it until it covers a ballroom. Small wrinkles become spread out, the overall surface appears flatter, and anything rare or unwanted becomes diluted until it is almost impossible to find. This same stretching also helps with the flatness problem. Any curved surface, if enlarged enough, can appear flatter over a small region. Earth is round, but the ground beneath your feet usually feels flat because you're seeing only a tiny part of a much larger surface. Inflation applies a similar idea to the geometry of space. If the early universe had some curvature, an enormous burst of expansion would stretch it so much that the observable part would look extremely flat. We may be seeing only a small region of a much larger cosmic whole, smoothed and flattened by inflation. The strange balance of the present universe would not require such delicate initial tuning, because inflation naturally drives space toward the kind of large-scale flatness we observe. The dilution of unwanted relics works in a similar way. If rare heavy particles or defects formed before inflation, the rapid expansion would spread them so thinly across space that the chance of finding one in our observable region could become tiny. They might still exist somewhere far beyond what we can see, or they may have become irrelevant to the part of the universe available to us. In this way, inflation acts like an enormous cosmic tidying process. It does not tidy in the human sense, of course. It does not fold socks or clear old cups from a desk, which would be appreciated, but perhaps outside its field of expertise. It smooths, stretches, flattens, and dilutes through the expansion of space itself. But what could cause such an extraordinary expansion? The most common versions of inflation involve a field, often called the inflaton field. A field in physics is not like a meadow, though the word may make it sound pleasantly grassy. It is something that has a value throughout space and can carry energy. The electromagnetic field is one example. Fields are part of the basic language of modern physics. In inflationary models, the inflaton field had a special kind of energy that acted almost like a temporary fuel for the rapid expansion of space. Instead of thinning out quickly as space expanded, this energy remained nearly constant for a brief period, driving the expansion faster and faster. This is where the story becomes especially strange. In ordinary life, when something expands, its contents usually become more spread out and less dense. If you spray perfume in a room, it disperses. If bread dough rises, the raisins move farther apart. But the energy associated with the inflaton field behaves differently in these models. As space expands, the field energy continues to fill the new space in a way that sustains the expansion. This leads to a feedback effect. More space appears, still containing the field energy, and that energy drives more expansion. It is not an explosion from a center. It is a rapid swelling of space everywhere in the affected region. The universe grows not because matter is thrown outward, but because the distances built into space increase at an incredible pace. Inflation did not last long. In fact, it had to end. A universe that remained in inflation forever, at least in our region, would never form atoms, stars, planets, or sleepy human minds wondering whether they have left the kettle on. At some point, the inflaton field changed state, releasing its energy into particles and radiation. This process is often called reheating. The name can be slightly confusing because the universe had been extremely hot before inflation, and inflation would have diluted and cooled whatever particles were already present. When inflation ended, the energy that had driven the expansion was converted into the hot mixture of particles and radiation that continued the standard Big Bang evolution. In this sense, the hot early universe we often describe may have been the aftermath of inflation ending. Inflation sets the stage, and reheating fills that stage with the energetic contents that later become matter and light. This means the phrase Big Bang can refer to different things depending on how carefully someone is speaking. In older popular descriptions, the Big Bang is the beginning of the hot dense expansion. In inflationary cosmology, the hot dense state may begin after inflation, when the energy of the inflaton field turns into particles. The absolute beginning, if there was one, remains uncertain. Inflation is not necessarily the first event. It is a proposed early phase that may explain why the universe looks the way it does. It pushes some questions back rather than removing them entirely. What started inflation? What was the inflaton field exactly? Why did it have the right properties? Why did it end when it did? These are still open questions. A good theory solves problems, but it usually leaves a few new ones sitting nearby looking innocent. One of the most important features of inflation is that it does not make the universe perfectly smooth. That would be a problem. If the universe were perfectly smooth, gravity would have nothing to grip, matter would remain evenly spread, and no galaxies would form. We need small irregularities. We need slightly denser places and slightly less dense places. Inflation provides a remarkable way to create them. Quantum fluctuations in the inflaton field, tiny variations that are unavoidable in quantum physics, would have been stretched by inflation from microscopic scales to cosmic scales. Once stretched, they became differences in density across the early universe. These differences were very small, but they were enough. Over millions and billions of years, gravity amplified them. Slightly denser regions pulled in more matter. Gas collected. Stars formed, galaxies gathered. The cosmic web emerged. This is one of the most beautiful connections in modern cosmology, not in a vague or decorative sense, but in a clear scientific one. The largest structures in the universe may have grown from the smallest possible fluctuations. The seeds of galaxies may have begun as quantum variations during inflation. This idea links the world of quantum physics, where uncertainty and fields dominate, to the immense architecture of galaxy clusters and cosmic voids. It suggests that the sky is not only old, but also carries a magnified record of tiny early disturbances. When scientists map the cosmic microwave background, they are seeing patterns that inflation may have stretched into place. Those faint temperature variations are not random background clutter. They're clues to the earliest physical processes we can hope to study. The cosmic microwave background is especially important because it provides a snapshot of the universe when it was much older than inflation but still young in cosmic terms. By the time that light was released, the universe had cooled enough for neutral atoms to form. The photons that had been trapped in the hot plasma could finally travel freely. That ancient light has crossed space ever since, stretched by the expansion of the universe into microwaves. When we measure its tiny variations, we are not seeing inflation directly, but we are seeing the later imprint of the fluctuations that inflation may have produced. The pattern of those variations matches many inflationary predictions very well. The universe appears nearly flat. The fluctuations are close to the kind expected from stretched quantum variations. The overall smoothness is exactly the kind of thing inflation was designed to explain. Still, scientists are careful. Inflation is widely studied and strongly supported by several broad observations, but the specific details remain uncertain. There are many different models of inflation. They differ in the nature of the inflaton field, how inflation began, how long it lasted, how it ended, and what additional signals it might leave behind. Some models predict a background of gravitational waves from the inflationary period. Detecting such a signal would be a major breakthrough. These gravitational waves would be ripples in spacetime generated by the rapid expansion and quantum processes of the early universe. They could leave a subtle pattern in the polarization of the cosmic microwave background. Scientists have searched for this pattern, and the work continues, but separating a primordial signal from foreground effects such as dust in our own galaxy is extremely difficult. The universe keeps its oldest receipts in a drawer full of lint. If primordial gravitational waves are found with the right properties, they could tell us about the energy scale of inflation and bring us closer to understanding the physics of the earliest universe. If they are not found, some inflationary models would be ruled out while others might survive. This is how science progresses, not usually with a single dramatic answer, but with careful narrowing. A theory makes predictions, observations test them. Some possibilities fade, others become stronger. Inflation has already passed important tests, but it is not a finished subject. It remains an active field full of models, debates, refinements, and attempts to connect the early universe with particle physics. There is another consequence of inflation that is both fascinating and difficult. In some versions, inflation does not end everywhere at once. It ends in some regions, creating hot Big Bang-like bubbles, while continuing elsewhere. This is called eternal inflation. If true, our observable universe may be one region where inflation ended, while far beyond our horizon, other regions formed with their own histories. Some people connect this to the idea of a multiverse. It is an exciting possibility, but it is also hard to test because those other regions may be permanently beyond observation. Science can consider such ideas, but it must handle them carefully. A possibility is not the same as a confirmed feature of reality. The line between bold theory and speculation must remain visible, even when the speculation is very interesting and wearing an impressive cosmic hat. The idea that space stretched faster than thought also changes how we picture size. When we say the early universe was tiny, we usually mean the part that became our observable universe was once compressed into a much smaller region. Inflation says that this region could have started extremely small and then expanded to an enormous scale in a tiny fraction of time. But the entire universe could be much larger than the observable universe, perhaps even infinite. The observable universe is simply the region from which light has had time to reach us since the early hot phase. Inflation may have stretched space so much that what we can observe is only a minute portion of the whole. There may be regions forever beyond our view, not because our telescopes are poor, but because the structure of space-time and the expansion of the cosmos prevent their light from ever arriving. This is a humbling thought. The universe we can see is already vast beyond easy comprehension. It contains hundreds of billions of galaxies, each with countless stars. Yet inflation suggests that the observable universe may be only a small patch of a much larger reality. It is not that we are at the centre. Every observer sees themselves at the centre of their observable region, simply because observation is limited by the distance light has travelled. We are not special in location. We are special only in the ordinary and tender sense that any conscious observer is special to themselves at bedtime. As rapid as inflation was, its legacy is patient. It shaped conditions that unfolded slowly afterward. Once inflation ended and reheating filled the universe with particles and radiation, The cosmos entered the hot, dense phase that led to the formation of protons, neutrons, light nuclei, atoms, stars, and galaxies. Inflation did not directly make stars. It did not directly make atoms. It did something earlier and more foundational. It set the large-scale smoothness. It stretched space toward flatness. It spread out unwanted relics. It turned quantum fluctuations into cosmic seeds. It prepared the initial conditions for the later universe to develop structure. In that sense, inflation is less like the construction of a building and more like the preparation of the ground on which every later building could stand. There is a common misunderstanding worth clearing away gently. Inflation does not mean the universe expanded into a larger empty region outside itself. It also does not mean there was a single central point from which everything rushed outward. The expansion happened everywhere within space. Every region moved away from every sufficiently distant region as distances grew. If you imagine dots painted on the surface of a balloon as it inflates, each dot sees other dots moving away. No dot on the surface is the center of the expansion. The comparison is useful, though not perfect, because the balloon's surface is two-dimensional and it expands into the air around it, while our space has 3 dimensions and need not expand into anything external. Still, the image helps remove the false idea of a cosmic blast from a central location. The phrase faster than light also needs care. In relativity, nothing can travel through its local space faster than light. But space itself can expand in such a way that distant regions separate faster than light. This already happens today for galaxies beyond certain cosmic distances. They are not breaking the local speed limit. The space between us and them is expanding. Inflation was an extreme early version of this principle. It stretched distances so dramatically that regions once close together became vastly separated. The result is a universe that looks smooth and flat across our observable patch, while still carrying tiny fluctuations that later grew into structure. As we let the idea settle, it may help to think of inflation not as an optional decorative detail, but as a proposed solution to deep problems in the early universe. Without it, the smoothness of the cosmic microwave background is hard to explain. The flatness of space looks unusually fine-tuned. Some predicted relics should be more common than they are. With inflation, these puzzles become connected. A brief burst of rapid expansion can explain them together. That is why inflation became such a central idea in cosmology. It does not answer everything, but it turns several separate mysteries into consequences of one early process. And yet, the end of inflation is just as important as inflation itself. Once the rapid stretching stopped, the universe had to become hot and filled with particles. Energy that had been stored in the inflaton field transferred into the contents of the cosmos. This reheating stage marks the beginning of the more familiar hot Big Bang evolution. The universe became a dense sea of particles, antiparticles, and radiation. Matter and antimatter interacted. Some tiny imbalance left matter behind. Quarks became bound into protons and neutrons. The stage was now set for the next major transformation, when the universe, still far too hot for atoms, began building the first stable ingredients of matter from a plasma of particles. Space had stretched with almost unimaginable speed, smoothing and preparing the cosmos, but now the story turns toward what filled that space. As energy became particles, particles found stability, and the young universe moved from a field-driven expansion into the hot, dense furnace from which the first matter would emerge. As inflation faded and its driving energy poured back into the young universe, the cosmos entered a state that was almost impossible to compare with anything familiar. Space had stretched enormously, smoothing and flattening the region that would become our observable universe. But it was not left empty and quiet afterward. The end of inflation filled the universe with an intense bath of particles, antiparticles, and radiation. It was like the lights had come on in a room that had no walls, no corners, and no furniture. except the lights were not really lights yet in the everyday sense, and the room was all of space, and the furniture had not been invented because atoms were still far in the future. So perhaps not very much like a room after all, but the universe has never been especially concerned with helping our metaphors behave. What mattered now was heat. The universe was unbelievably hot, not hot like a desert road or a furnace or the centre of a star, but hot in the deep physical sense that every particle and field carried enormous energy. At such temperatures, the familiar structures of matter could not hold together. Atoms would have been impossible. Even atomic nuclei could not yet survive. The universe was not made of little solar systems of electrons orbiting nuclei, which is already an oversimplified image for atoms anyway. It was a dense, blazing mixture of more basic ingredients, with particles colliding, transforming, appearing, disappearing, and sharing energy in a restless cosmic crowd. Everything was changing too quickly for the universe to settle into the kind of calm matter we know from tables, teacups, planets, and slightly misplaced reading glasses. To understand this period, it helps to remember that particles in modern physics are not tiny marbles in the old-fashioned sense. They are excitations of underlying fields. A field can fill space, and a particle is like a little localized ripple or packet of energy in that field. This may sound strange, but it is one of the most successful ideas in physics. The electron field gives rise to electrons. Quark fields give rise to quarks. Other fields produce other particles. In the early universe, these fields were extremely energetic. The heat of the cosmos meant that particles were constantly being produced from energy and then converted back again through collisions. Nothing was sitting still. Nothing was waiting politely in a line. If the early universe had a personality at this stage, it was not calm. It was a crowded kitchen during a dinner rush, except the cooks were quantum fields and the soup was reality. Among the most important ingredients were quarks and gluons. Quarks are fundamental particles that later become locked inside protons and neutrons. Gluons are associated with the strong nuclear force, the interaction that binds quarks together. Today, quarks are never found freely under normal conditions. They are confined inside particles such as protons and neutrons. But in the early universe, the temperature was so high that quarks and gluons moved in a dense shared state, often called a quark-gluon plasma. This was not a plasma in the everyday sense of a glowing gas in a lamp. It was a far more extreme state of matter, where the usual boundaries of protons and neutrons had not yet formed. The universe was too hot for quarks to remain confined in the stable packages we know today. As space expanded, the cosmic temperature fell. This cooling did not happen because heat escaped somewhere outside the universe. There was no outside refrigerator, no cosmic window left open by mistake. The universe cooled because space itself expanded. Radiation stretched, energies decreased, interactions changed. This cooling was creative. It allowed structures that had been impossible to become possible. When the universe was hot enough, quarks could not settle into protons and neutrons. When it cooled past a certain stage, the strong nuclear force confined quarks into these composite particles. In that moment, the universe gained some of the basic building blocks that would later matter enormously. Protons and neutrons are not atoms, but without them atoms could never appear. A proton is a positively charged particle that forms the nucleus of hydrogen and appears in the nuclei of all other atoms. A neutron is electrically neutral and helps build the nuclei of most elements beyond ordinary hydrogen. In the early universe, protons and neutrons formed from quarks as the universe cooled. They emerged into a sea still filled with radiation, electrons, positrons, neutrinos, and other particles. Positrons are the antimatter partners of electrons. Neutrinos are extremely light particles that interact so weakly that they can pass through ordinary matter almost as though it is not there. Even today, huge numbers of neutrinos pass through your body every second, which sounds rude until you realize they almost never disturb anything. In the early universe, however, everything was so dense and hot that even neutrinos were part of the general thermal crowd, interacting more often than they do now. At the same time, the universe contained both matter and antimatter. For nearly every kind of matter particle, there is an antimatter counterpart. When a particle meets its antiparticle, they can annihilate, converting their mass and energy into radiation or other particles. In the early universe, energy was so abundant that matter and antimatter pairs could form readily. For a while, creation and annihilation balanced each other in a kind of furious rhythm. Energy became particles, particles became energy. The cosmic mixture remained in constant exchange. This is one reason the early universe was so different from the present. Today, if an electron and a positron meet, the event is special enough to notice in a detector. Back then, such processes were part of the background traffic. Here we meet one of the most important mysteries in all cosmology. If matter and antimatter had been created in exactly equal amounts, they should have annihilated almost completely as the universe cooled. The result would have been a universe filled mostly with radiation, with almost no matter left to make galaxies, stars, planets, or patient listeners. But that is clearly not the universe we inhabit. Matter survived. Antimatter did not survive in comparable amounts. This means there must have been a tiny imbalance in the early universe, a slight excess of matter over antimatter, not a large excess, not a dramatic victory, just a tiny difference, enough that after matter and antimatter annihilated in huge numbers, a small remainder of matter was left behind. That leftover is everything we see as ordinary matter today. This is both scientifically profound and strangely humbling. The material world exists because the early universe was not perfectly symmetrical between matter and antimatter. Every star, every planet, every leaf, every book, every sleepy hand resting on a blanket comes from that small surviving excess. Physicists have proposed mechanisms that could create such an imbalance, involving processes that treat matter and antimatter slightly differently. We know that nature does allow some small differences between matter and antimatter behaviour, but whether the known differences are enough to explain the entire cosmic imbalance remains an open question. The existence of matter is obvious. The reason there is enough of it is still being investigated. It is one of those cases where the universe gives us the answer in the form of our own existence, then refuses to show all of its working. As the universe cooled further, many particles disappeared from the common mixture. Heavy, unstable particles decayed into lighter ones. Matter and antimatter pairs annihilated as there was no longer enough energy in the cooling universe to keep recreating them in the same numbers. Photons, the particles of light, remained extremely abundant. But light at this stage did not travel freely across the universe in the way it does now. The universe was still a dense plasma of charged particles. Photons were constantly scattered by electrons and other charged particles. They could move, but not far in a straight line before being redirected. The cosmos was bright in the sense of being filled with radiation, but it was not transparent. It was more like a glowing fog with no clear view through it. The cooling universe also changed the balance between protons and neutrons. In the earlier stages after they formed, protons and neutrons could transform into one another through interactions involving the weak nuclear force. While the universe was hot and dense enough, these transformations happened often enough to maintain a kind of balance. But as the universe expanded and cooled, the interaction slowed. Eventually the balance froze out, meaning that the changing conditions no longer allowed protons and neutrons to shift back and forth as efficiently. Protons became more common than neutrons. This mattered because the number of neutrons available would later help determine how much helium and other light nuclei could form. Neutrons outside nuclei are not stable forever. Left alone, they decay into protons and other particles, so there was a race of sorts, though not a race with flags, lanes, or anyone making encouraging noises from the sidelines. The universe needed to cool enough for nuclei to form before too many neutrons decayed away. But it could not form stable nuclei immediately because the radiation was still too energetic. Any fragile early nucleus would be smashed apart by high-energy photons almost as soon as it formed. This delay is often described as a bottleneck. The universe had protons and neutrons, but it was still too hot for them to assemble into lasting nuclei in large amounts. The simplest nucleus is just a single proton, which is hydrogen in its most basic form. But to build helium and other light nuclei, protons and neutrons first had to combine into a fragile pair. That pair could not survive while the universe remained too hot. Once the temperature dropped enough, these pairs could remain intact long enough for further nuclear reactions to occur. Then a short but important period of light element formation began. Protons and neutrons combined into nuclei of hydrogen, helium, and small traces of other light elements. This process is one of the great successes of Big Bang cosmology. The predicted amounts of these light elements match what we observe in the universe remarkably well, especially when we look at old, relatively unprocessed material that has not been heavily altered by generations of stars. It is important not to rush past what was and was not being made. The early universe did not create carbon, oxygen, iron, gold, or the full chemical richness of the later cosmos in significant amounts. Conditions were changing too quickly, and the universe was not yet a place where heavy element formation could proceed in the way it does inside stars. The Big Bang mainly produced hydrogen and helium, with tiny amounts of a few other light elements. The heavier elements would come later, after gravity gathered gas into the first stars and those stars began nuclear fusion in their cores. So when we say the first particles led to matter, we are not yet talking about the chemistry of life. We're talking about the simplest physical ingredients from which much later complexity could grow. The formation of a light nuclei happened when the universe was still extremely young, only minutes old. That is almost impossible to absorb. Human minutes are slow things. They are enough time to make tea, miss a bus, or wonder why a computer update is taking longer than promised. Cosmic minutes near the beginning were different. In those first minutes, the broad chemical composition of the universe was set. Most ordinary matter became hydrogen nuclei. A substantial portion became helium nuclei. Small traces of other light nuclei were also formed. After that brief period, the universe became too cool and too spread out for further Big Bang nuclear reactions to continue efficiently. The recipe was largely fixed. The universe had made its first simple nuclei and then moved on. But atoms still could not exist. This is the key point for this part of the story. A nucleus is not an atom. An atom requires electrons bound to nuclei, forming neutral structures that can interact chemically. The early universe still contained free electrons moving through a sea of radiation. Photons were energetic enough to knock electrons away whenever they tried to settle onto nuclei. Imagine trying to place a hat on someone in the middle of a hurricane made of light. The hat may be perfectly good, the head may be available, but the conditions are not supportive. In the early universe, electrons could not remain attached to nuclei for long. The cosmos stayed ionized, meaning matter existed as charged particles rather than neutral atoms. Because charged particles scatter light very effectively, the universe remained opaque. Photons could not simply stream across space. They bounced and scattered through the plasma. This is why there is no ordinary light from the very first minutes reaching our telescopes directly. The universe was not transparent yet. It would take hundreds of thousands of years of expansion and cooling before electrons could finally bind to nuclei in a stable way. Only then would photons be released to travel freely, creating the ancient background glow we can observe today. Before that time, the universe was like a luminous fog whose contents were real and active, but whose light could not escape in a clean, straight path. There is something wonderfully counterintuitive here. The early universe was full of light, but no one could have seen through it. Again, there was no one to see, but even in principle, visibility requires transparency, not merely brightness. A thick fog can glow with headlights and still hide the road. The young universe was glowing everywhere, with radiation interacting constantly with charged particles. It had energy, heat, motion, and structure beginning in the smallest differences, but it did not have clear space in the visual sense. The darkness of the later night sky would only become possible after the universe cooled enough for light to travel freely, and after stars eventually formed to shine in that darkness. The particles present in this era also included neutrinos, and their story quietly separated from the rest. As the universe expanded, neutrinos eventually stopped interacting frequently with other matter and radiation. They decoupled, meaning they began travelling largely undisturbed through space. In principle, there should be a cosmic background of ancient neutrinos from the early universe, much like the cosmic microwave background of photons from a later time. Detecting this neutrino background directly is extremely difficult because neutrinos interact so weakly, but its existence is supported indirectly by cosmological evidence. It is another reminder that the early universe left more than one kind of relic. Some relics are light we can map, some are particle backgrounds we infer, some are patterns in matter spread across enormous distances. As the universe became cooler and less dense, it also became less able to maintain the constant transformations of its earliest moments. This is an important theme. In the hottest era, particles were in a state of rapid exchange. Interactions happened constantly. Different forms of energy and matter remained closely linked, but expansion gradually pulled processes apart. Some reactions became too slow compared with the pace of cosmic change. Some particles decayed, some annihilated, some froze into lasting abundances. The history of the early universe is partly the history of things falling out of equilibrium. The cosmos cooled, and with each cooling step, a new kind of permanence became possible. That word permanence should be used gently. Nothing in the universe is permanent in the deepest sense, but compared with the frantic first instance, protons are impressively stable. Hydrogen nuclei formed in the early universe still exist today. Some of the hydrogen in your body, in water and in the sun has an origin reaching back to this period. The heavier elements in your body were mostly made later in stars, but the hydrogen is older than any star. It comes from the early universe itself. Every sip of water contains hydrogen whose nucleus belongs to the first few minutes of cosmic history. That is a quiet thought, and perhaps a good one to keep nearby when daily life feels too narrow. Ordinary things carry ancient timelines. A glass of water is not just local. It is cosmological, though it rarely mentions this unless encouraged. The universe after these first particles and nuclei formed was still not ready for stars. It was expanding, cooling, and filled mostly with hydrogen nuclei, helium nuclei, electrons, photons, neutrinos, and dark matter. Dark matter deserves mention here because it was also present, though its exact nature remains unknown. Dark matter does not emit or absorb light in ordinary ways, but it has gravity. It appears to make up a significant portion of the matter in the universe. In the early cosmos, dark matter would have contributed to the growth of structure by gathering gravitationally, helping create the scaffolding into which ordinary matter later fell. We do not yet know what dark matter is made of. It may be a new kind of particle, or perhaps something more surprising. But its gravitational role in cosmic history seems essential. While ordinary matter was coupled tightly to radiation before atoms formed, dark matter could begin clumping under gravity earlier because it did not interact strongly with light. This difference mattered later. The tiny density variations stretched by inflation became slight differences in the distribution of matter and dark matter. Over time, dark matter helped deepen gravitational wells, regions where ordinary matter would later collect once it was free from the constant pressure and scattering of radiation. So even in the era before atoms, the seeds of structure were already present. The universe was not yet building galaxies, but the groundwork for galaxy formation was being laid quietly in the pattern of density differences. The first particles era is therefore not just a list of ingredients. It is a transformation from pure energetic possibility toward the first stable material foundation. Quarks became bound into protons and neutrons. Matter survived over antimatter by a tiny excess. Neutrons and protons later formed light nuclei. Electrons remained free. photons remained trapped in the plasma. Neutrinos slipped away into their own nearly invisible background. Dark matter began its gravitational work. The universe was still far too hot for atoms, far too uniform for galaxies, and far too bright to be transparent, but it was no longer the same as it had been in the first tiny fraction of a second. It had acquired lasting ingredients. There is a kind of patience built into the cosmic story at this point. After the dramatic speed of inflation and the rapid formation of particles and light nuclei, the universe entered a long waiting period. Not waiting with intention, of course. The universe was not checking its watch or wondering whether atoms might hurry along. It was simply expanding and cooling. For hundreds of thousands of years, photons scattered through the plasma. Electrons remained unbound. Nuclei drifted among radiation. Matter could not yet form neutral atoms. The conditions had to soften. The energetic light had to lose enough strength. The cosmic fog had to thin in just the right physical way. And this is where the next great change begins to approach. The universe already has nuclei. It already has electrons. It already has radiation everywhere. But the pieces cannot yet settle into neutral atoms because the heat is still too intense. Once expansion cools the cosmos enough, electrons will finally remain bound to nuclei. The charged fog will clear. Photons will stop scattering constantly and begin travelling freely across space. That ancient light, released when the universe becomes transparent, will continue across billions of years, stretched and cooled by expansion, until it reaches our instruments as a faint glow from every direction. The universe is still opaque for now, still too hot for atoms, still a luminous plasma of charged particles and restless radiation, but the slow cooling of space is carrying it toward the moment when light itself will be allowed to travel. For a very long time after the first particles and light nuclei formed, the universe was bright, hot, and strangely impossible to see through. That may sound contradictory, because we often think brightness and visibility are the same thing. A room is dark, then a lamp turns on, and suddenly the furniture appears, including the chair you forgot was slightly too close to your shin. But the early universe was not like a room waiting for a lamp. It was filled everywhere with radiation, and yet that radiation could not travel freely. Light was constantly being scattered, redirected, absorbed, and re-emitted by the charged particles around it. The universe glowed, but it was opaque. It was not dark in the ordinary sense. It was more like a dense, shining fog, with no clear path for a beam of light to cross great distances without being interrupted. This period lasted far longer than the first furious moments of cosmic history. The first particles formed quickly. The first light nuclei formed within the first few minutes. But atoms, real neutral atoms with electrons settled around nuclei, took much longer. The universe had to expand and cool for hundreds of thousands of years before that could happen. Compared with the age of the universe today, that is still very young, a kind of cosmic infancy. Compared with the first second, it is an immense stretch of time. The early universe had moved from explosive rapid change into a slower phase, where the main task was simply cooling enough for matter and light to separate from one another. At the start of this long waiting period, the universe was filled mostly with hydrogen nuclei, helium nuclei, free electrons, photons, neutrinos, and dark matter. The hydrogen nuclei were mostly single protons. The helium nuclei were made of 2 protons and 2 neutrons, though we do not need any formal notation for them. The electrons were not bound to the nuclei. They moved freely through the plasma, and because they carried electric charge, they interacted strongly with photons. A photon trying to travel through this early plasma did not get very far before meeting an electron and scattering in a new direction. The photon might head one way, scatter, head another way, scatter again, and keep repeating this process. The result was that light remained trapped in the cosmic fog. This is a key point. The universe was full of photons, but it was not transparent to them. Transparency is not about whether light exists. It is about whether light can move freely without being constantly disturbed. The air in your room is transparent because visible light can pass through it with very little scattering. A cloud is not transparent because droplets scatter light in many directions. The early universe was much denser and more energetic than any cloud, and its free electrons were extremely effective at scattering light. If there had been an eye floating there, which there was not because eyes require atoms, molecules, cells, evolution, and a surprising amount of maintenance, it would not have seen distant objects. There were no distant objects to see, and light itself could not carry a clear image across space. The universe was also still very hot. Whenever an electron tried to join a nucleus, an energetic photon could strike it and knock it away again. This prevented stable atoms from forming. The ingredients were present, but the conditions were wrong. A hydrogen nucleus and an electron could meet, but the surrounding radiation was too intense for the relationship to last. It was less like building matter, and more like trying to stack papers in a strong wind while someone nearby keeps opening another window. The structure could begin, but it could not remain. As space expanded, the radiation filling the universe lost energy. Photons stretched along with the expansion of space, and stretched photons are less energetic. The temperature of the cosmic radiation fell. This cooling slowly made it easier for electrons to remain attached to nuclei. Eventually, the universe reached a point where photons no longer had enough energy, on average, to keep tearing atoms apart as quickly as they formed. Electrons began to settle around nuclei. Hydrogen atoms formed in great numbers. Helium nuclei captured electrons as well. The universe became filled with neutral atoms rather than a plasma of free-charged particles. This event is often called recombination, though the name is a little misleading. The electrons and nuclei were not recombining in the sense of returning to an earlier atomic state, because stable neutral atoms had not existed before in the history of the universe. It is one of those scientific names that survives because everyone knows what it means once they have learned it, even if the first impression is not quite right. A more descriptive phrase would be the time when electrons first combined with nuclei in a lasting way, but scientists prefer shorter names because otherwise every paper would need a larger cover. The formation of neutral atoms changed the universe dramatically. Free electrons had scattered photons very efficiently. Neutral atoms did not. Once electrons were bound into atoms, the fog cleared. Photons that had been constantly redirected could now travel long distances through space. Light decoupled from matter. The universe became transparent. This was not like someone flipping a switch in a dark room, and it was not exactly instant everywhere in the simple sense. It was a transition that occurred over a period of time as the universe cooled through the right conditions. But in cosmic history, it was sharp enough to leave a clear surface in the past from which the ancient light we observe today last scattered. That ancient light is now known as the cosmic microwave background. It is one of the most important pieces of evidence for the Big Bang model. It is not light from stars, it is older than stars. It is the leftover radiation from the time when the universe first became transparent. At the moment it was released, it would have been visible as a warm glow, though again there were no eyes to see it. Over billions of years, the expansion of the universe stretched that light. Its wavelengths grew longer and longer. What began as a much hotter glow has cooled into microwave radiation, a faint signal that fills the sky in every direction. When scientists first detected this background radiation in the 20th century, it was a major confirmation of the hot early universe. The discovery was not made by people looking at a beautiful telescope image of the young cosmos. It involved radio equipment, unexpected noise, careful measurement, and at one point a great deal of concern about whether pigeons had made a mess inside an antenna. The universe sometimes reveals its deepest history through very undignified practical problems. But once the signal was understood, its meaning was profound. Space was filled with a faint thermal glow, almost exactly the kind expected if the universe had once been hot, dense and opaque, then cooled enough for light to travel freely. The cosmic microwave background is often described as the afterglow of the Big Bang, But it is worth being precise. It is not light from the first instant. It does not show us the universe at the moment of origin. It comes from much later, when the universe was hundreds of thousands of years old. That is still extremely early compared with the present age of nearly 14 billion years, but it is not the beginning itself. Before that time, the universe was opaque to photons. We cannot see earlier with ordinary light because ordinary light could not travel freely earlier. The cosmic microwave background is therefore like a wall of light in the past. It is the earliest light that can reach us directly. This wall is not a physical wall in space. It is a surface in time, the distance from which photons have been travelling toward us since matter and radiation decoupled. When we look in any direction, we see this ancient radiation arriving from the distant past. Because light takes time to travel, looking far away is also looking back in time. The cosmic microwave background surrounds us not because we are at the centre of the universe, but because every observer is surrounded by the most distant light that has had time to reach them. An observer in a faraway galaxy would see their own sphere of ancient background radiation around them. The effect comes from the age of the universe and the finite speed of light, not from any special location. What makes the cosmic microwave background especially valuable is not just that it exists, but that it is incredibly uniform while also being slightly uneven. Its temperature is almost the same in every direction, which supports the idea that the early universe was remarkably smooth. But it is not perfectly the same. There are tiny variations, small differences in temperature from one patch of sky to another. These variations are extremely small, but they are essential. They represent slight differences in density and energy in the early universe. Over time, those small differences grew under gravity into the large-scale structure we see today. Without them, matter would have remained too evenly spread. With them, gravity had something to work on. This is where the story connects back to inflation. Inflation may have stretched tiny quantum fluctuations into the large-scale patterns that later appeared in the cosmic microwave background. When that ancient light was released, it carried an imprint of those variations. The slightly warmer and cooler patches in the background are not random decoration. They are records of early density differences, acoustic waves in the hot plasma, and the conditions from which galaxies eventually formed. Scientists study these patterns with extraordinary care because they contain information about the composition, age, geometry, and early history of the universe. Before recombination, ordinary matter and radiation were tightly linked. Photons pushed on charged particles, and charged particles pulled through gravity. The early plasma supported waves, somewhat like sound waves, though not sound travelling through air. These were pressure waves moving through the hot mixture of photons and matter. Gravity tried to pull matter into denser regions, while radiation pressure pushed back. This created oscillations in the plasma. When the universe became transparent, the state of those oscillations was frozen into the pattern of the cosmic microwave background. Later, related patterns influenced how galaxies would be distributed across space. In this way, the universe carries an early rhythm in its structure, although not a rhythm you could tap on a table, unless your table is several 100 million light-years wide, in which case there may be other concerns. The precision with which the cosmic microwave background has been measured is remarkable. Space missions and ground-based observatories have mapped it in great detail. These maps show a universe that was nearly uniform, with tiny variations at the level needed to seed structure. From those patterns, cosmologists can infer how much ordinary matter the universe contains, how much dark matter, how much dark energy, how close space is to flat, and how old the universe is. A faint microwave glow, cooler than almost anything in daily life, carries information from a time when the cosmos was a hot plasma. It is one of the great examples of the universe preserving memory through physics rather than intention. The transition to transparency also marks a change in the role of ordinary matter. Before this moment, ordinary matter was strongly coupled to radiation. The pressure of light resisted the collapse of matter into dense structures. Dark matter, which does not interact with light in the same way, had already begun gathering under gravity into invisible clumps and filaments. After photons decoupled, ordinary matter was freed from the constant push and drag of radiation. It could begin falling more effectively into the gravitational wells shaped by dark matter. This did not produce stars immediately. The universe still needed time. Gas had to gather, cool, and collapse, but the release of light allowed matter to start behaving in a new way. Structure formation could proceed more strongly. At the same time, the universe entered a period sometimes called the Cosmic Dark Ages. The name sounds dramatic, but it describes something simple. After the cosmic microwave background photons were released, there were still no stars. The universe was now transparent, and it was filled mostly with neutral hydrogen and helium gas, along with dark matter and radiation. The ancient glow was fading and stretching into longer wavelengths as space expanded. No new starlight had yet appeared. There was no sun, no galaxy, no glowing nebula, no familiar night sky. There was matter, gravity, and time, but not yet the first stellar fires. The cosmos had become transparent, but it had not yet become illuminated by stars. This is a subtle but important distinction. The phrase "let there be light" might suggest that this was when light first existed. It was not. Light had existed earlier, abundantly. The difference was that light could now travel. The universe became transparent to its own radiation. Later, the first stars would create new sources of light. But the clearing of the cosmic fog came before the first stars. It is like a theatre becoming clear of smoke before the actors arrive on stage. The room is visible, but the performance has not yet begun. The matter left behind after a combination was mostly hydrogen and helium. These atoms formed a thin gas spread through the expanding universe, thin by ordinary standards, but not empty. The gas was slightly denser in some regions than others because of the early fluctuations imprinted in the cosmic microwave background. Gravity slowly amplified those differences. Denser regions attracted more matter. Dark matter gathered into halos, large invisible structures that provided gravitational wells. Ordinary gas fell into those wells, gradually collecting in greater amounts. But gas does not automatically form stars. It must lose energy, cool, and become dense enough for gravity to overcome pressure. This took time. The cosmic microwave background continued travelling. Every photon moved freely after its last scattering, crossing the expanding universe while its wavelength stretched. Today, when our instruments detect that radiation, they're receiving photons that have been travelling for nearly the entire age of the universe. They arrive from all directions, faint and cold, carrying the image of the universe as it was when transparency began. In a sense, the night sky is layered. Nearby stars show us relatively recent light. Distant galaxies show us older light. The cosmic microwave background shows us the oldest direct light available to ordinary telescopes. Beyond it lies an earlier universe that light cannot reveal directly. To study earlier times, scientists must rely on other evidence. They use the abundance of light elements to infer what happened during the first minutes. They use particle physics to understand hotter earlier states. They search for gravitational waves that might carry information from even earlier periods, because gravitational waves could travel through conditions that trapped light. They study the large-scale distribution of matter for clues about the initial fluctuations. But the cosmic microwave background remains the great visual boundary. It is as though the universe, after hundreds of thousands of years of being unreadable to light, finally became clear enough to take a photograph. Of course, it was not a photograph in the usual sense. There was no camera outside the universe, no cosmic parent asking the infant cosmos to hold still and smile. The image is reconstructed from radiation reaching us now. Each direction in the sky corresponds to light from a different region of that ancient surface. By mapping the temperature and polarization of that light, scientists build a picture of the early universe. Polarization, the orientation of light waves, carries additional information about the scattering processes that occurred at the time of release and about the matter distribution that affected the light on its journey. These details help refine our understanding of cosmic history. The background is not only a glow, it is a data set written across the entire sky. There is a quiet beauty in how ordinary atoms made transparency possible. Once electrons joined nuclei, the universe changed from a charged plasma into a neutral gas. That sounds like a technical shift, but its consequences were enormous. Photons were released. Matter began to fall more freely into dark matter structures. The earliest observable light began its journey. The conditions for later star formation were established. The universe became a place where distance could be seen across, where future stars could shine through space, where galaxies could eventually become visible to one another. Before atoms, light was trapped. After atoms, light could become a messenger. The formation of atoms also begins the long road toward chemistry, though chemistry in any rich sense was still far away. Hydrogen and helium atoms are simple. Hydrogen can later participate in many chemical compounds, but in the young post-recombination universe, there were no planets, no dust grains, no heavy elements in significant amounts. Helium is even less chemically eager. The early neutral gas was therefore chemically plain. It had the simplicity of a universe not yet processed by stars, but that simplicity was exactly what gravity needed to begin the next stage. Large clouds of hydrogen and helium could gather. In dense enough regions, they could eventually heat as they collapsed, leading to the birth of the first stars. Those stars would then begin making heavier elements, changing the chemical future of the cosmos. When we consider transparency, it is useful to notice how much depended on timing. If the universe had expanded differently, if the density had been different, if matter and radiation had remained coupled for longer or separated earlier, the growth of structure would have changed. The cosmic microwave background would have a different pattern. The formation of galaxies might proceed differently. Cosmology is the study not only of what exists, but of the sequence that allowed it to exist. Each stage opens the next. Inflation stretches fluctuations. Particle processes produce matter and light nuclei. Recombination releases light and frees ordinary matter from radiation pressure. Gravitational collapse then slowly works on the gas. The universe does not jump directly from the Big Bang to stars. It passes through a series of physical thresholds. For a listener today, the release of the cosmic microwave background may feel remote, but it is directly observable. Turn a sensitive microwave telescope toward any part of the sky, after accounting for nearby sources and foreground signals, and the ancient glow is there. It fills space. It is not a mythic remnant or a metaphor. It is measurable radiation with a near-perfect thermal spectrum, exactly the kind expected from a hot, dense early universe that cooled over time. This is one reason the Big Bang model is so strong. It predicted a relic glow before it was discovered. When scientists found it, the discovery fit the model in a deep and specific way. Later measurements of its tiny variations made the evidence even stronger. The universe at the moment of transparency was still much smaller than it is now, but it was already enormous compared with human scales. It was filled with matter and radiation, almost uniform, but not perfectly so. Its temperature had fallen enough for neutral atoms to form. The photons released then did not know, of course, that they would one day be used by small living beings on a rocky planet to estimate the age and composition of the cosmos. Photons are not known for long-term planning. They simply travelled, stretched by expanding space, passing through regions that would later become galaxies and clusters, crossing billions of years until some of them entered detectors designed by a species that had only recently learned to stop arguing with sundials. As transparency began, the universe became less like a glowing fog and more like an open field of neutral gas, though still without stars. The ancient radiation streamed away in all directions. Matter, now less tied to light, started to respond more fully to gravity. dark matter structures continued to deepen. Slightly denser regions became the places where gas would collect. The cosmos was entering a quieter stage, but quiet does not mean unimportant. The dramatic heat of the first minutes had passed. The sudden release of light had occurred. Now gravity would take its time. It would work patiently, pulling matter into larger and larger concentrations, preparing the first dense clouds that would eventually ignite. This next period was long and dim. The cosmic microwave background faded into colder wavelengths as the universe expanded. Neutral hydrogen filled space. No stars had yet formed to produce visible light. There were no galaxies with spiral arms, no supernova, no planets, no warm surfaces under skies. Yet within the slight unevenness of matter, the future was already taking shape. The seeds had been planted by early fluctuations marked in ancient light and strengthened by dark matter. Transparency had allowed radiation to escape and matter to begin its slower gravitational work. The universe had learned, in a physical sense, how to become see-through. Now it had to learn how to shine again, not with trapped primordial radiation, but with the first stars forming out of darkness. After the universe became transparent, something almost eerie followed. Light could finally travel freely, but there were no stars yet to make new light. The ancient glow that had been released when atoms formed was already stretching into longer and colder wavelengths as space expanded. The universe was no longer a hot, opaque fog, but it was not yet the brilliant place we see in telescope images. It was filled mostly with neutral hydrogen and helium, spread thinly through space, along with invisible dark matter shaping gravity in the background. There were no galaxies as we know them, no shining suns, no planets, no dust clouds glowing pink and blue in photographs, and no night sky filled with points of light. There was only gas, gravity, darkness, and time. This period is often called the Cosmic Dark Ages, and the name is fairly accurate, though it can make the universe sound as if it had simply gone to bed for a while. In a way, perhaps it had. The first great brightness of the hot early universe had faded from direct visible light, and the later brightness of stars had not yet arrived. Space was transparent, but there was little to see. The universe had the ingredients for future structure, but those ingredients had not yet gathered into the dense glowing objects that would transform cosmic history. It was a quiet era, not because nothing was happening, but because the processes that mattered were slow, hidden, and gravitational. Gravity was the patient worker of this age. In the early universe, matter had not been perfectly smooth. Tiny variations had been left behind, faint differences in density that showed up in the cosmic microwave background as tiny temperature variations. Those small differences were enough. Where matter was slightly denser, gravity pulled in more matter. Where dark matter had already begun to gather into invisible clumps, ordinary gas could slowly fall inward. Dark matter played a crucial role, because it did not interact with light in the same way ordinary matter did. Before atoms formed, ordinary matter was closely tied to radiation, but dark matter was freer to begin clumping under gravity earlier. By the time the universe became transparent, dark matter had already begun building a kind of hidden scaffolding. This scaffolding was not made of beams or walls, of course. It was a network of gravitational wells, regions where matter felt a stronger pull. Ordinary hydrogen and helium gas gradually fell into these wells. At first, the gas was spread out and thin. It did not collapse into stars instantly. Gas has pressure, and pressure resists collapse. To form a star, gas must gather and become dense enough that gravity wins. It must also cool, because hot gas pushes outward more strongly. Cooling allows a cloud to contract further. In the present universe, gas clouds often cool with the help of heavier elements and dust grains, but the early universe had almost none of those. The first gas clouds were made mostly of hydrogen and helium, which are not especially efficient at losing heat under those conditions. So the first star formation was difficult. The universe had to work with a very simple recipe. A small amount of molecular hydrogen helped. ordinary hydrogen atoms can pair up into hydrogen molecules, and those molecules can radiate energy away more effectively than individual atoms in certain conditions. This cooling was important for the earliest clouds. Without it, many gas clouds would have remained too warm and too resistant to collapse. But even with molecular hydrogen, early cooling was limited compared with later star-forming regions enriched by heavier elements. That meant the first stars probably formed in relatively massive clouds, and may themselves have been very massive compared with many stars today. They were not like the Sun in all respects. They were born in a universe with no previous generations of stars, no carbon, no oxygen, no iron, no rocky dust, and no planets orbiting quietly nearby. They were the first stellar fires made from almost pure primordial gas. It took a long time for the first stars to appear, perhaps tens or hundreds of millions of years after the early hot phase, depending on the details of structure formation. That may sound slow, but on cosmic scales it was still early morning. The universe had expanded and cooled. Dark matter halos had grown. Gas had fallen inward, collected, and finally reached conditions where gravity could compress it enough to ignite nuclear fusion. Fusion is the process by which light atomic nuclei combine into heavier ones, releasing energy. In the cores of stars, this process produces the pressure and heat that allow a star to shine and resist gravitational collapse. The first stars marked a major turning point. For the first time since the fading of the primordial glow, the universe had new sources of light. Try to imagine that moment without making it too theatrical. There was no single first star lighting up the whole universe like a match in a dark room. The universe is too large, and star formation would have happened in many places as conditions became right. But somewhere, in one of the earliest dense clouds of hydrogen and helium, gravity pulled gas inward until the core became hot and dense enough for fusion to begin. A star switched on, then others followed. In the surrounding darkness, light began to spread from these first stellar objects, travelling through transparent space, interacting with the gas around them, changing the universe not all at once but region by region. These first stars are often called population 3 stars, a slightly confusing name because they came first. Astronomers use the term population 1 for relatively metal-rich stars like the Sun, population 2 for older metal-poor stars, and population 3 for the first stars with essentially no heavy elements. In astronomy, metals means elements heavier than hydrogen and helium, which is a little alarming to chemists but quite normal in astrophysics. By that definition, oxygen is a metal, carbon is a metal, and if you object, the stars will not mind. Population 3 stars would have formed from the clean material left by the Big Bang, before stellar furnaces had enriched the cosmos with heavier elements. Because they had so few heavy elements, these first stars likely behaved differently from stars that formed later. Heavy elements help gas cool and fragment into smaller clumps. Without them, early gas clouds may have produced larger stars. Many of the first stars may have been extremely massive, shining fiercely and burning through their fuel quickly. Massive stars live fast lives. They are bright, hot, powerful, and short-lived. They do not last billions of years like small, quiet stars. Some may survive only a few million years before ending violently. A few million years sounds long from the point of view of a person, waiting for a reply to an important message, but for a star it can be brief. The Sun has already lived for billions of years and is middle-aged. A massive first star might be born, shine intensely, and die before the universe had much time to get used to it. Their deaths mattered just as much as their lives. When massive stars exhaust their nuclear fuel, their cores can collapse, and they can explode as supernovae. Some of the earliest massive stars may have ended in especially energetic explosions, scattering newly made heavy elements into surrounding space. Others may have collapsed directly into black holes, contributing to the early population of black holes that may later have helped seed galaxies or grow into supermassive black holes. The details are still an area of active research because the first stars are extremely difficult to observe directly. They formed long ago, far away, and lived briefly. We infer their properties through theory, simulations, observations of ancient stars, and attempts to see the earliest galaxies with powerful telescopes. The first stars began the chemical transformation of the universe. Before them, the cosmos was mostly hydrogen and helium, with tiny traces of a few light elements. After them, heavier elements began to appear. In their cores, stars fused lighter nuclei into heavier ones. In their explosions, some produced and scattered elements that would later become part of new stars, planets, and living things. Carbon, oxygen, silicon, iron, and many other elements entered cosmic circulation through stellar processes. The universe became less chemically plain. It gained the raw materials for rocky worlds, atmospheres, oceans, and eventually biology. The Big Bang made the simplest ingredients. The first stars began the long work of enrichment. This enrichment changed how later stars formed. Once heavy elements and dust existed, gas clouds could cool more efficiently. Cooler gas can fragment into smaller pieces, making lower mass stars more common. That means later generations of stars could be more varied, including long-lived stars that still shine today. Some of the oldest stars in our galaxy contain very little heavy element material, and by studying them, astronomers can learn about the early stages of chemical enrichment. These ancient stars are like cosmic archives. They formed from gas that had been touched by only a few earlier stellar generations, perhaps even by the first explosions. Their chemical compositions preserve clues about what those first stars were like. The first stars also changed the state of the gas between galaxies. Their ultraviolet light was powerful enough to affect surrounding hydrogen atoms. Remember that after the universe became transparent, most ordinary matter was neutral hydrogen and helium gas. Neutral hydrogen can absorb certain kinds of ultraviolet light. The first stars poured energetic radiation into their surroundings, stripping electrons from hydrogen atoms and turning the gas back into an ionized state in expanding bubbles around the first luminous objects. This process is called reionization. It did not happen everywhere at once. The universe was too vast and uneven for that. Instead, bubbles of ionized gas formed around early stars and galaxies, grew, overlapped, and gradually transformed the intergalactic medium. Reionization was one of the major transitions in cosmic history. First, the universe was an ionized plasma before atoms formed. Then it became neutral when electrons joined nuclei and light travelled freely. Later, the first stars and galaxies ionized much of the hydrogen again. The word reionization refers to that second ionization. It sounds like the universe changed its mind, and in a physical sense it did. The neutral gas of the cosmic dark ages became increasingly exposed to energetic starlight. The darkness ended not with one sunrise, but with many growing regions of light and ionized gas spreading through space. This process took hundreds of millions of years. It depended not only on the first stars, but also on the first galaxies and perhaps early black holes. As stars formed in groups within dark matter halos, those groups became the earliest galaxies or protogalaxies. They were likely small and irregular compared with many galaxies today. They merged with one another over time, building larger structures. Gravity does not assemble the universe neatly in one step. It builds hierarchically. Small structures form first, then merge and grow into larger ones. The galaxies we see today, including our own Milky Way, have long histories shaped by mergers, gas flows, star formation, and dark matter. The earliest galaxies would have been busy places. Gas fell inward. Stars formed. Massive stars exploded. Heavy elements spread. Radiation escaped into surrounding space. Some regions may have formed black holes from the collapse of massive stars. Those black holes could pull in gas, heat it, and produce radiation. Over time, some black holes grew enormously, becoming the supermassive black holes found at the centers of large galaxies. One of the current puzzles in astronomy is how some supermassive black holes became so massive so early in cosmic history. Observations have found very distant quasars, powered by rapidly growing black holes, from times when the universe was still young. Explaining their growth requires either very efficient feeding, massive initial seeds, or other processes that are still being investigated. The early universe, once it began making structure, did not proceed timidly. The end of the cosmic dark ages was therefore not just about light appearing. It was about complexity beginning to accelerate. Stars created radiation. Radiation changed gas. Supernovae created heavy elements. Heavy elements changed future star formation. Black holes formed and grew. Galaxies merged and evolved. The universe moved from a simple gas-filled state into a web of luminous structure. The first stars were not merely lamps. They were engines of transformation. They heated, ionized, enriched, and stirred their surroundings. They made the universe chemically and physically more complicated. There is a gentle irony in the phrase cosmic darkness, because even during that time, the cosmic microwave background still filled the universe. It had not vanished. It was cooling and stretching, becoming less energetic as space expanded. But there were no stars shining in visible light, no galaxies blazing against blackness. The darkness refers to the absence of stellar light, not a complete absence of radiation. The universe was never truly empty or inactive. It was simply between luminous eras. The first glow of the hot Big Bang had been released and was fading into microwaves. The later glow of stars had not yet taken over. The first stars bridged that gap. Seeing this era directly is extremely difficult, but modern astronomy is beginning to approach it. The farther away we look, the farther back in time we see, because light takes time to reach us. Very distant galaxies show us the universe when it was young. Powerful space telescopes can detect galaxies from the first few 100 million years of cosmic history, giving clues about how early star formation and galaxy assembly happened. Astronomers also study how light from distant objects is absorbed by intervening hydrogen gas, because that absorption reveals the changing state of the universe during reionization. Radio astronomy may eventually map the neutral hydrogen from before and during this transition in great detail, allowing scientists to trace the cosmic dark ages and cosmic dawn more directly. Cosmic dawn is a fitting phrase for the appearance of the first stars and galaxies. It was not the beginning of the universe, and it was not the first light in all history, but it was the first starlight. It was the time when gravity had gathered enough matter into dense places for fusion to begin. Imagine the universe before that, transparent but unlit by stars, filled with thin neutral gas and invisible dark matter structures. Then imagine small regions beginning to shine, not everywhere at once, but scattered across the vastness. Around each early star or galaxy, radiation carved out bubbles in the neutral gas. Explosions spread the first heavy elements. More gas cooled, more stars formed. Bubbles grew and overlapped. Darkness gave way gradually to a universe with sources of light. The first stars also began the long chain that would lead to planets. This is easy to miss because planets did not appear immediately. The earliest stars probably had no rocky planets like Earth, because the necessary heavy elements were not yet available in large amounts. But when those stars died and scattered new elements, they enriched gas clouds from which later stars and planets could form. Each generation of stars changed the material available to the next. Eventually, after enough enrichment, dust grains and rocky solids could form around young stars. Planets could assemble in disks of gas and dust. Some worlds became rocky, some held water, some orbited at distances where temperatures allowed liquid water to persist. Much later, on at least one such world, chemistry crossed into biology, and biology eventually developed the habit of asking large questions while wrapped in blankets. The first stars are therefore ancestors, not in a personal family tree sense, but in a material one. They did not contain life, but they helped make life chemically possible. Without stars, the universe would have remained mostly hydrogen and helium. Hydrogen and helium are important, but they do not by themselves make forests, bones, oceans, or brains. The richness of ordinary experience depends on elements made after the Big Bang, inside stars and stellar explosions. The first stars began that enrichment. They were the first factories of complexity. Their light also shaped the appearance of the universe to future observers. Once galaxies formed and grew, the cosmos became filled with luminous islands. Large-scale structure emerged as matter collected along filaments and nodes shaped by dark matter. Galaxy clusters formed. Voids opened between dense regions. The cosmic web became more pronounced. The smooth early universe evolved into a textured one. Not random chaos, but structure grown from tiny initial differences. The same fluctuations visible in the cosmic microwave background eventually became the pattern of galaxies spread across space. In this way, the first stars were part of a larger gravitational story. They ignited in the densest early regions where matter had gathered first. It is worth pausing on how long the universe spent without stars. For us, a few 100 million years is almost beyond imagination. Human civilization is only a thin final line on the cosmic calendar. Yet for the universe, those starless ages were a beginning phase. The ingredients had to cool and collect. Gravity had to amplify small differences. Gas had to find its way into dark matter halos. Cooling processes had to allow collapse. Fusion had to ignite. Nothing in this sequence was rushed. After the violent speed of the first moments, the universe entered the slower discipline of structure formation. It is a reminder that not all important changes look dramatic while they are happening. Some of the most important work is done quietly, in the dark, by gravity. And then, once stars began, the darkness did not simply vanish. Light travelled outward, but space was huge. Neutral hydrogen absorbed some radiation. Early stars lived and died. Galaxies formed unevenly. Some regions became ionized earlier than others. Reionization was patchy, gradual, and complex. The universe became transparent to more kinds of light over time, as neutral hydrogen was cleared from the spaces between galaxies. By the time reionization was complete, the intergalactic medium had been transformed. Starlight and radiation from early galaxies could travel more freely across vast distances. The universe had moved from dark ages into a luminous cosmic era. The stars that ended the darkness are mostly gone now. If they were as massive as many models suggest, they burned out quickly and left no surviving examples for us to inspect directly. We search for their fingerprints instead. We look at extremely ancient stars that may carry chemical traces of the first supernova. We search for distant galaxies whose light has travelled from near cosmic dawn. We model how primordial gas collapses. We measure the timing and progress of reionization. We watch for signals from neutral hydrogen that may reveal the distribution of matter before the first galaxies fully lit the universe. The first stars are hidden, but not entirely beyond reach. Their effects are written into the later cosmos. There is a peaceful way to think about this stage. The universe had become transparent, but transparency alone did not make it bright. It needed gravity to gather matter. It needed gas to cool. It needed the first stars to ignite. Then it needed those stars to live, die, and enrich space. What we now see as a universe full of galaxies is the result of many linked processes. The Big Bang did not produce galaxies fully formed. It produced the conditions from which galaxies could grow. The first stars were one of the first great signs that growth had begun. By the time the cosmic darkness was ending, the universe had changed from a nearly uniform sea of gas into a place with luminous structure. There were early galaxies, hot massive stars, expanding bubbles of ionized hydrogen, the first heavy elements spreading into space, and perhaps the first growing black holes. The universe was still young, but it was no longer simple. The story had moved from expansion and cooling into formation and transformation. Matter was no longer just drifting in a smooth background. It was gathering, shining, exploding, and changing its surroundings. From here, it becomes important to clear away a few common misunderstandings, because the story of the Big Bang is often compressed into images that are easy to remember but not quite right. The Big Bang was not a normal explosion. It did not happen at one central point in empty space. It did not immediately create stars, galaxies, planets, or all the elements in the periodic table. It did not make light appear only once in a simple dramatic flash. Light existed early, became trapped, was released when the universe became transparent, and later was produced again by the first stars. The real story is richer than the shortcut version, and as the first stars begin to shine through the thinning cosmic dark ages, the next step is to untangle what the Big Bang was not, so the picture left behind is clearer, steadier, and much closer to what the evidence actually tells us. It is worth slowing down here, because the Big Bang is one of those ideas that almost everyone has heard of, and almost everyone has been given a slightly misleading picture of it at some point. That is not because people are careless, or because science teachers are secretly trying to confuse everyone before lunch. It is because the real idea is difficult to fit into a quick image. Human minds like scenes. We like a place, a before, an after, a thing happening somewhere, and preferably a sensible direction in which it is happening. The Big Bang does not cooperate with that instinct. It was not a normal explosion. It was not a fireball in empty space. It was not matter bursting outward from one central point. It was not a moment when fully formed galaxies came flying out like sparks. It was not even a bang in the ordinary sense, because sound needs a medium to travel through and something to hear it. The name is memorable, but the event itself was not a cosmic firecracker with dramatic echo and smoke. The most common misunderstanding is the simplest one. People imagine all matter gathered into a tiny dot somewhere in a vast black emptiness, and then suddenly that dot explodes. Pieces fly outward, stars and galaxies scatter in all directions, space already exists around it, like a dark room waiting for the explosion to fill it. This image feels natural because it resembles explosions we know. A firework explodes in the sky. A volcano throws material into the air. A glass breaks and shards spread across the floor, usually at exactly the moment you are trying to have a peaceful evening. In all of these examples, something expands into a space that is already there. There is a centre, an outside, and a surrounding environment. The Big Bang was not like that. According to the standard cosmological picture, the early universe was not matter expanding into space, it was space itself expanding. The distances between regions grew because the geometry of the universe changed. There was no central point in space where the Big Bang happened. The Big Bang happened everywhere, because every region of space we can observe today was once part of that earlier hot, dense state. The place where you are now was not outside the Big Bang looking in. It was inside the early universe, just as every place was. If we trace the expansion backward, distant galaxies were closer together, radiation was hotter, matter was denser, and eventually the whole observable universe was compressed into a much smaller, hotter, more uniform condition. But that compression applies to all of space in the observable region, not to a little bomb sitting in a larger room. A helpful comparison is the surface of a balloon with dots drawn on it, but the comparison must be used carefully. As the balloon inflates, each dot moves away from the others. No dot on the surface is the center of the expansion. The distance between the dots increases because the surface stretches. In a similar way, distant galaxies move away from one another because space expands. But the balloon has limitations as a picture. The surface of the balloon is two-dimensional, while our space has 3 dimensions. The balloon expands into the air around it, while the universe does not need an outside space in the same ordinary sense. Still, the comparison helps remove the false idea of a central explosion. If every dot sees other dots moving away, that does not mean each dot is the center in some special way. It means the whole surface is expanding. This leads to another common misconception. People sometimes ask where the Big Bang happened, as though astronomers might point to a direction in the sky and say, over there, behind that galaxy, just to the left of the cosmic curtains. But there is no location like that. The Big Bang was not an event at one point in space. It was an earlier state of the entire observable universe. When we look far away, we look back in time because light takes time to reach us. In every direction, if we look far enough, we see the ancient glow of the cosmic microwave background, the light released when the universe became transparent. That glow surrounds us not because we are at the center of the explosion, but because every observer in the universe would see their own sphere of ancient light from the time when photons began traveling freely. The evidence comes from all directions because the early hot dense state was everywhere. Another misunderstanding is that the Big Bang explains why there is something rather than nothing in the deepest philosophical sense. It may eventually connect with that question, but the standard Big Bang model is more specific. It describes how the universe evolved from an early hot dense state into the expanding, cooling universe we observe today. It does not fully explain the absolute origin of existence. It does not tell us with certainty what happened at the first instant, if there was a first instant. It does not settle whether time began there, whether there was an earlier phase, whether there was a bounce, or whether a deeper theory of quantum gravity will change the picture. The Big Bang model is powerful because it explains a vast amount of evidence after the earliest uncertain boundary, but it is not a complete answer to every question about why reality exists at all. This is not a weakness in the way people sometimes assume. A scientific model can be extremely successful while still having limits. Newton's laws describe everyday motion wonderfully well, but they are not the full story at high speeds or strong gravity. Relativity describes gravity and space-time with great success, but it does not yet fully merge with quantum physics. The Big Bang model describes the expansion and cooling of the universe from an early hot dense state, the formation of light elements, the release of the cosmic microwave background, and the growth of large-scale structure. These are enormous achievements, but when people ask what came before or why there is a universe at all, they're asking questions that reach beyond the standard model into active research and philosophy. It is better to say that clearly than to pretend the beginning has been completely wrapped up and filed away. The Big Bang also was not the creation of all elements in the universe. This is a very common shortcut. People hear that the universe began with the Big Bang and assume everything in it was made right there, including oxygen, carbon, iron, gold, and all the other elements that make the world interesting and occasionally expensive. In reality, the early universe mainly produced hydrogen and helium, with tiny traces of a few other light elements. The heavier elements came later, inside stars and during stellar explosions and other energetic astrophysical events. The carbon in living things, the oxygen in water, the calcium in bones and the iron in blood were not all forged in the Big Bang itself. They are products of later cosmic history. This matters because it shows that the universe became chemically rich over time. The Big Bang provided the simplest material foundation. The first stars took that material and transformed some of it through nuclear fusion. When massive stars died, they scattered heavier elements into space. Later generations of stars and planets formed from gas enriched by those earlier stellar lives and deaths. Our own solar system formed billions of years after the Big Bang from a cloud that already contained heavy elements made by previous stars. So the Big Bang was not a complete construction event where the universe instantly received its full inventory. It was the beginning of a long chain of physical processes. The universe did not start with everything ready. It started with conditions that allowed later complexity to develop. Nor did the Big Bang immediately produce stars and galaxies. This is another image that sneaks into the imagination. We picture the early explosion sending out stars in all directions like glowing embers, but stars came much later. First there was the hot dense state, then particles, then light nuclei, then a long period when the universe was a hot plasma, opaque to light. Then neutral atoms formed and the cosmic microwave background was released. Then came the cosmic dark ages, when the universe was transparent but not yet filled with stars. Gravity slowly gathered gas into dark matter halos. Only after enough time did the first stars ignite. Galaxies formed gradually through the growth and merging of smaller structures. The universe we see now, with its spirals, clusters, and bright stellar populations, is the result of billions of years of development. The Big Bang was also not a claim that the universe expanded from a dot into nearby emptiness in the way an object expands. When cosmologists say the observable universe was once extremely small, they mean that the distances between the matter and radiation in our observable region were once much smaller. But the whole universe may be far larger than the observable universe, and it may even be infinite. If the universe is infinite today, it could have been infinite in the past as well, with every part much denser and hotter. This is hard to picture because we tend to think small means having an edge. But an infinite universe can still expand. The distances between points can grow even if the total extent is infinite. Infinity does not need to become bigger in the everyday sense for the scale of distances inside it to change. This is one of those ideas that makes the brain look for a chair. The Big Bang was not the discovery that Earth or our galaxy is at the centre of everything. In fact, modern cosmology strongly moves away from that kind of centrality. The expansion looks broadly the same from any galaxy, at least on large enough scales. Wherever an observer is located, distant galaxies will appear to recede. This is not because every location is magically the special centre, it is because space expands everywhere. The old idea that we occupy a privileged central position has been replaced by a more humble and more elegant view. We are in one region of a vast universe that appears broadly uniform on very large scales. Our location matters to us, because of course it does, but cosmologically it does not appear to be the centre of expansion. Another misconception is that galaxies move away from us through space in exactly the same way that shrapnel moves away from an explosion. Nearby galaxies can have their own motions due to gravity, and some, like the Andromeda Galaxy, are moving toward us because local gravitational attraction dominates over cosmic expansion at that scale. But on very large scales, the recession of distant galaxies is mainly due to the expansion of space itself. The light from distant galaxies is stretched as space expands during its journey, shifting it toward longer wavelengths. This stretching is one of the major pieces of evidence that the universe is expanding. It's not simply that galaxies were thrown outward long ago and are now coasting through a static background. Space itself is changing. The Big Bang was not a process that finished and then stopped. The early hot dense phase ended, yes. The universe cooled, it became transparent, stars and galaxies formed. But the expansion of the universe continues. In fact, observations show that the expansion is currently accelerating on large scales, a discovery connected to what we call dark energy. Dark energy is still not fully understood, but its effects appear in the way distant supernovae and the large-scale structure of the universe behave. This means the Big Bang is not merely a past event like a match being struck and then forgotten. It is the beginning of an ongoing cosmic evolution. We live in the aftermath, and the aftermath is still unfolding. It is also not accurate to say that the Big Bang was disproved by the fact that we cannot see the exact first moment. Science often works from indirect evidence. We cannot watch the core of the sun directly with ordinary eyes, but we understand it through light, neutrinos, helioseismology, and physics. We cannot watch atoms with bare senses, but their behaviour is measurable. We cannot see the first moments of the universe with ordinary light because the early universe was opaque before the cosmic microwave background was released. But we can study the evidence those early stages left behind. The expansion of the universe, the cosmic microwave background, the abundance of light elements, and the distribution of galaxies all point toward a hotter, denser past. The inability to see the exact first instant does not erase that evidence. It simply marks the boundary. where deeper theory is needed. Another point often misunderstood is the role of cosmic microwave background radiation. Some people think of it as debris from an explosion, like ash drifting through space. It is better understood as ancient light from the time when the universe became transparent. Before neutral atoms formed, photons scattered constantly from free electrons. Once electrons joined nuclei, photons could travel freely. That light has been travelling ever since, stretched by cosmic expansion into microwaves. It is not smoke, it is not leftover sparks, it is a relic radiation field, a thermal afterglow from a time when the universe was hot, dense, and filled with plasma. Its nearly uniform temperature and tiny variations are among the strongest evidence for the early hot universe. The Big Bang was not a religious or anti-religious statement by itself. People sometimes try to pull it immediately into arguments about creation, meaning, or belief. Those are important questions for many people, but scientifically the Big Bang model is a physical theory about cosmic evolution. It is based on observations and mathematical models. Different people interpret its philosophical meaning differently. Some see it as compatible with spiritual ideas. Others see it as a purely natural account. Science itself does not settle every metaphysical interpretation. It tells us what the evidence indicates about the physical history of the universe. Keeping those categories clear helps prevent confusion. Cosmology is already difficult enough without asking it to do everyone else's arguments at the same time. The Big Bang also was not a perfect explanation from the moment it was proposed. The model developed over time through observation, debate, correction, and refinement. Early ideas about an expanding universe emerged from general relativity and the observed recession of galaxies. The prediction and later discovery of the cosmic microwave background strengthened the model dramatically. Measurements of light element abundances added support. Later observations of the microwave background's tiny fluctuations refined the picture further. Inflation was introduced to solve problems in the simpler model, such as the horizon and flatness problems. Dark matter and dark energy became necessary to explain the behaviour of galaxies, clusters, cosmic structure, and expansion. The modern Big Bang model is not one single old idea frozen in place. It is a developing scientific framework shaped by evidence. It was also not accepted simply because it sounded dramatic. In fact, the phrase Big Bang was originally used in a somewhat dismissive way by a critic of the idea. The name stuck because it was vivid, not because it was technically perfect. Scientists did not adopt the model because the phrase was catchy. They adopted and refined it because the evidence became strong. The universe is expanding. It contains a relic radiation field with the expected properties. Its light elements match predictions from early nuclear reactions. Its large-scale structure grows naturally from small early fluctuations. These facts are the real foundation. The name is just the label on the box, and like many labels, it is a little misleading if you stare at it too long. The Big Bang was not the end of mystery. This may be the most important misconception of all. Sometimes science is presented as if each explanation simply removes wonder. The opposite is usually true. Understanding that the Big Bang was an expansion of space rather than an explosion into space does not make it less astonishing. It makes it more astonishing. Realizing that atoms formed hundreds of thousands of years later, that stars came after cosmic darkness, that heavier elements were forged in stellar interiors, that galaxies grew from tiny fluctuations, and that the observable universe may be only a small part of a much larger whole does not shrink the story. It deepens it. The universe is not less mysterious when we describe it more accurately. It becomes mysterious in better focus. A clearer picture also protects us from false puzzles. If someone asks what the Big Bang exploded into, the answer is that this assumes the wrong kind of explosion. If someone asks where in space it happened, the answer is that it happened everywhere in the early universe. If someone asks why we're at the centre, the answer is that we're not. If someone asks why there were already galaxies at the first moment, the answer is that there were not. If someone asks why the Big Bang made gold and oxygen, The answer is that stars and stellar explosions did most of that later work. Many confusing questions become easier once the misleading picture is replaced. By now, the story has become less like a single blast and more like a sequence. The early universe was hot, dense, and expanding. It may have undergone inflation, stretching space and magnifying tiny fluctuations. Energy became particles. Matter survived over antimatter by a small imbalance. Protons and neutrons formed. Light nuclei formed in the first minutes. The universe remained a hot, opaque plasma for hundreds of thousands of years. Electrons joined nuclei to form neutral atoms. Light began travelling freely as the cosmic microwave background. Darkness followed before the first stars. Gravity gathered gas into the first luminous structures. Stars enriched the universe with heavier elements. Galaxies grew. Planets came much later. Life came in later still. The Big Bang was the beginning of this physical history as far as our well-supported models can trace it, not a finished universe emerging fully assembled. That distinction makes the evidence even more meaningful. When we detect the cosmic microwave background, we're not seeing an artist's impression. We are measuring ancient radiation. When we calculate the abundance of helium, we're not guessing randomly. We're testing the conditions of the early universe. When we observe distant galaxies, we're watching earlier stages of cosmic development because their light has taken so long to reach us. When we map the large-scale structure of the universe, we are seeing the grown-up form of tiny early differences. Each line of evidence supports a universe that has evolved over time from a hotter, denser state into the complex cosmos around us. So what was the Big Bang not? It was not a noise, not a firework, not an explosion from a centre, not matter flying into pre-existing emptiness, not the instant creation of stars, planets and heavy elements, not proof that we sit at the centre of the cosmos, not a complete explanation of why existence exists, not a simple story with every question answered. It was, as far as the evidence shows, the early hot dense expansion of space itself, followed by cooling, particle formation, nuclear reactions, transparency, darkness, stars, galaxies, and everything that came after. The true picture is harder to draw on a classroom board, but it is far more interesting, and with the false images gently set aside, the evidence becomes easier to appreciate. The Big Bang is not believed because someone liked the sound of a beginning. It is supported because the universe still carries records of its earlier state. The galaxies are moving in a pattern that reveals expansion. The sky is filled with an ancient microwave glow. The light elements preserve the memory of early nuclear reactions. The large-scale structure of galaxies reflects tiny primordial variations. Even now, in every direction, the cosmos is offering clues about what it once was. Having cleared away what the Big Bang was not, we can turn toward those clues themselves, the signals still around us, the measurements that let scientists reconstruct a history no human witnessed, and the quiet cosmic echo that continues to arrive from the time when the universe first became transparent. Now that the louder misunderstandings have been set aside, the question becomes quieter and more interesting. How do we actually know any of this happened? No one stood outside the universe with a clipboard. No telescope can look all the way back to the absolute first instant. No photograph exists of space beginning to expand, and no ancient observer left a note saying that the universe was very hot today, and likely to remain scientifically important. Yet cosmology is not a story invented to fill the dark. It is built from evidence, and the evidence is still around us. It arrives in light stretched across space. It appears in the motion of galaxies. It glows faintly in microwaves from every direction. It hides in the amounts of hydrogen and helium. It shapes the web of galaxies spread across the observable universe. The Big Bang is not accepted because it sounds dramatic. It is accepted because several independent clues all point back to the same strange conclusion. The universe was once hotter, denser, smoother and smaller in scale, and it has been expanding and cooling ever since. The first clue is expansion. When astronomers look at distant galaxies, they find that most of them are moving away from us, and the farther away they are, the faster they appear to recede. This does not mean Earth is sitting proudly at the centre of a cosmic escape scene, watching everything flee our social awkwardness. It means space itself is expanding. From any galaxy, distant galaxies would appear to be moving away. The expansion is not centred on us. It is a feature of the universe on large scales. The light from those galaxies is stretched as space expands during its journey, shifting it toward longer wavelengths. This stretching is called redshift, and it tells us that the universe is not static. It is changing with time. If the universe is expanding now, then the natural next step is to run the story backward. Not literally, of course. We cannot make the galaxies reverse like a film, though it would make telescope scheduling more exciting. But mathematically and observationally, an expanding universe implies that in the past, galaxies were closer together. Matter was denser, radiation was hotter. The farther back we go, the more compressed the universe becomes. This is the basic doorway into the Big Bang model. Expansion today points to a hotter, denser yesterday, and then to an even hotter, denser earlier universe. It does not by itself tell us everything about the first moment, but it tells us that the cosmos has a history, and that the past was physically different from the present. For a long time, some scientists preferred the idea of a steady-state universe, one that expands but always maintains the same overall appearance because new matter is continuously created. It was an elegant attempt to avoid a beginning and keep the universe eternally similar on large scales, but observations did not favour it. As telescopes looked deeper into space, they also looked further back in time, and they found that the universe changed. Distant galaxies were not exactly like nearby galaxies. Quasars and young galaxies were more common in earlier eras. The cosmos had evolved. The steady-state picture began to struggle, while the Big Bang model became stronger. The universe did not simply exist forever in the same condition. It had a hot, dense past and a developing history. The second great clue is the cosmic microwave background, the ancient afterglow from when the universe first became transparent. This is one of the most powerful pieces of evidence in all of cosmology. Before neutral atoms formed, the universe was a hot plasma of free electrons and nuclei, and light could not travel freely. Photons were constantly scattered by charged particles. Then, after hundreds of thousands of years of expansion and cooling, electrons joined nuclei to form neutral atoms. The fog cleared. Light decoupled from matter and began travelling across space. That light has been moving ever since, stretched by the expansion of the universe into faint microwave radiation. When this background radiation was discovered, it was a turning point. The Big Bang model predicted that if the universe had once been hot and dense, there should be a leftover glow filling space. Not a glow from stars, not a local signal from our galaxy, a relic radiation field from the early universe itself. And there it was, arriving from every direction with almost the same temperature. The discovery was not glamorous in the usual cinematic way. It involved an antenna, persistent noise, careful checking, and the removal of some very unhelpful pigeon material. The universe, in its wisdom, sometimes hides the origin of everything behind a maintenance issue. But once understood, the signal was extraordinary. It matched what a hot early universe should leave behind. The cosmic microwave background is often called the baby picture of the universe, though it is not a picture of the first instant. It shows the universe when it was already hundreds of thousands of years old. By human standards, that is ancient. By cosmic standards, it is early infancy. Before that time, ordinary light could not travel freely, so we cannot see earlier with photons in the direct way. Still, this background is the oldest light available to telescopes, and it carries an astonishing amount of information. Its near uniformity tells us the early universe was extremely smooth. Its tiny variations tell us it was not perfectly smooth. Those small variations were essential because they became the seeds of galaxies and clusters. Modern maps of the cosmic microwave background show tiny differences in temperature across the sky. These differences are so small that they would be easy to dismiss if they were not so important. They reflect slight density variations in the early universe. Regions that were a little denser eventually attracted more matter through gravity. Over time, those small differences grew into the cosmic web of galaxies. The background radiation is therefore not just an old glow, it is a record of the initial pattern from which structure grew. When scientists study it, they can infer the universe's age, composition, geometry, and early conditions with remarkable precision. The sky is not merely dark above us. It is carrying a cooled, stretched message from the time when atoms first formed. The third clue comes from the light elements. The early universe was hot enough for nuclear reactions, but only for a short time. During the first few minutes, protons and neutrons combined to form the nuclei of light elements, mostly hydrogen and helium, with small traces of others. The Big Bang model predicts specific amounts of these early elements based on the density and temperature of the young universe. When astronomers measure the abundances of ancient gas, especially material that has not been heavily altered by stars, the results match the predictions very well. This is a major success. It means that the early universe was not only expanding and hot in a vague sense, it had the right conditions to produce the light element mixture we observe. This point is easy to overlook because hydrogen and helium sound plain. They are not as glittering as gold or as biologically dramatic as oxygen and carbon. But in cosmology, plain ingredients can be powerful evidence. If the universe had never been hot and dense, why would it contain so much helium in such a consistent ancient abundance? Stars make helium too, but not enough in the right way to explain the total. The early universe had to contribute. Big Bang nucleosynthesis, the formation of light nuclei in the first minutes, explains why hydrogen and helium dominate ordinary matter across the cosmos. Later stars built heavier elements, but the broad foundation was laid early. The fourth clue is the large-scale structure of the universe. Galaxies are not scattered randomly like crumbs after an unfortunate biscuit incident. They form a vast cosmic web. There are filaments, sheets, clusters, and enormous voids. This pattern grew from tiny early density variations under the influence of gravity. The same variations seen in the cosmic microwave background became, over billions of years, the structure mapped by galaxy surveys. Computer simulations that begin with small early fluctuations, dark matter, ordinary matter, and expanding space can reproduce the kind of cosmic web we observe. This connection between the early background glow and the later galaxy distribution is one of the great unifying achievements of modern cosmology. Dark matter plays a crucial role in this structure. It does not emit or absorb light in ordinary ways, but it has gravity. Without it, the growth of galaxies and clusters would be very difficult to explain. In the early universe, ordinary matter was coupled to radiation until atoms formed, but dark matter could begin clumping earlier. It created gravitational wells that ordinary matter later fell into. The pattern of galaxies today reflects this hidden scaffolding. We do not yet know exactly what dark matter is made of, and that remains one of the largest open questions in physics. But its gravitational effects are deeply woven into the evidence for cosmic history. The Big Bang model does not stand alone as a simple expansion story. It is connected to the measured contents of the universe, including ordinary matter, dark matter, radiation, and dark energy. The fifth clue comes from looking far away, which means looking back in time. Light travels at a finite speed, so when we observe distant galaxies, we see them as they were long ago. The deeper our telescopes look, the younger the universe appears. Nearby galaxies show us a relatively mature cosmos. Very distant galaxies show us earlier stages of galaxy formation. The most distant objects reveal a universe that was smaller, denser, more active in certain ways, and still assembling itself. This is exactly what the Big Bang model predicts. The universe should not look the same at all distances, because distance is also time. We should see cosmic evolution, and we do. Powerful telescopes have found galaxies from very early in cosmic history, helping scientists study the period when the first stars and galaxies were forming. These observations do not show the Big Bang itself, but they fill in the story between the cosmic microwave background and the mature universe around us. They show that galaxies grew over time. They reveal young systems rich in gas and intense star formation. They help trace how the cosmic dark ages ended and how reionization unfolded. Every distant galaxy is a time capsule, and together they make the universe less like a static scene and more like a developing biography. There is also evidence in how the expansion of the universe has changed over time. Observations of distant exploding stars known as supernovae showed that the expansion is accelerating today. This was surprising. Gravity should slow expansion if matter were the only major influence. The acceleration suggests the presence of dark energy, a mysterious component associated with the large-scale behavior of space itself. Dark energy was not part of the early simple Big Bang picture, but it is now part of the standard cosmological model because observations demand it. The universe's history includes not only early rapid expansion and later structure formation, but also a more recent era in which expansion began accelerating. This does not replace the Big Bang. It extends the story into the future and deepens the mystery of what space itself is doing. Each line of evidence would be impressive on its own. Together they become difficult to ignore. Expansion says the universe was denser in the past. The cosmic microwave background says it was once hot, opaque, and then became transparent. The light elements say nuclear reactions happened in the first minutes under specific conditions. The large-scale structure says tiny early fluctuations grew through gravity. Distant galaxies show cosmic evolution. These clues come from different observations, different instruments, different physical processes, and yet they agree. That agreement is what gives the Big Bang model its strength. Science trusts patterns that survive many independent tests. This does not mean every detail is settled. The earliest fraction of a second remains uncertain. Inflation is strongly motivated and supported by several observations, but its exact mechanism is not confirmed. The nature of dark matter is unknown. The nature of dark energy is unknown. The question of whether time began, whether there was a before, or whether our universe emerged from a deeper process remains open. But uncertainty at the frontier does not erase the evidence for the broad history. We can be confident that the universe was once hotter and denser, while still being honest that we do not know everything about the absolute origin. A map can be accurate over most of the landscape and still have clouds over the mountains. One of the most beautiful things about this evidence is that it is not hidden in one place. It is all around us. The expansion is seen in the light of galaxies. The cosmic microwave background fills the sky. The light elements are spread across ancient gas and stars. The galaxy web stretches through the observable universe. The story is not locked away in a single artifact. The universe itself is the artifact. It carries memory in its radiation, chemistry, motion, and structure. Cosmologists are not guessing from silence. They are reading a record written at different scales. There is a gentle lesson in the cosmic microwave background especially. The oldest light we can see is not bright to our eyes. It does not dazzle the night. It is cold, faint, and stretched into wavelengths our bodies cannot sense directly. Without instruments, we would never know it was there. Yet it surrounds us continuously. Every moment, ancient photons from the early universe pass through the space around Earth. Some are detected by satellites and telescopes, most simply continue onward. They began their journey when the universe first became transparent, long before stars like the Sun existed, long before the Milky Way took its present form, long before Earth formed, long before life appeared. They arrive now, quiet messengers from a time when matter and light parted ways. This is why the phrase echo still around us feels right, though it is not an echo of sound. It is an echo in radiation, in structure, in abundance, in expansion. The Big Bang was not noisy, but it left traces. The universe does not speak, but it preserves. It stretches light without losing the information completely. It lets gravity amplify tiny variations. It locks early nuclear history into element ratios. It turns ancient conditions into modern measurements. The evidence is not a single shout from the beginning, but a collection of soft signals that become clear when heard together. And perhaps this is the most calming part of the whole subject. We live in a universe that can be understood, at least partly, from inside itself. We're not outside looking down at the full shape of time. We are small observers on one planet, orbiting one star, inside one galaxy among many. Our lives are brief compared with cosmic ages. Our instruments are fragile. Our theories are incomplete. And still, by measuring light, motion, chemistry, and structure, we have reconstructed a history reaching back nearly to the beginning of the observable universe. That is an astonishing achievement, not because it makes us masters of the cosmos, but because it shows that careful attention can carry the mind across billions of years. So when someone asks how we know the Big Bang happened, the answer is not that we saw it directly. We did not. The answer is that the universe today behaves like a universe with a hot, dense past. Its galaxies recede, its light is stretched, its sky glows with ancient microwaves. Its simplest elements appear in the predicted amounts. Its galaxies grew from tiny early differences. Its distant past looks younger than its nearby present. Each clue points backward. Each one supports the others. Together they form a coherent picture of a universe that has expanded, cooled, formed matter, released light, gathered stars, built galaxies, and eventually produced the conditions for worlds like ours. Now, after travelling from the uncertainty before the beginning, through the first tiny moments, the rapid stretching of space, the formation of particles, the release of ancient light, the first stars, and the clearing away of common myths, we return to the quiet place where we started. You are here in the late universe, made of atoms with long histories. Some of the hydrogen in you belongs to the early minutes after the Big Bang. The heavier elements in you were made later in stars. The light reaching your eyes from the sky carries time inside it. The darkness between stars is not emptiness without a story. It is space shaped by expansion, crossed by old radiation, threaded by gravity, and filled with traces of everything that came before. And if tonight's journey has helped your thoughts settle, if the beginning of everything has somehow made the room feel softer rather than larger and colder, then I would be grateful if you gave the video a like, subscribed, or shared this quiet corner of science with someone who might enjoy drifting through the universe at a gentler pace. The Big Bang was not a simple blast, and it was not the end of mystery. It was the start of a long unfolding, one that continues in every galaxy, every star, every atom, and every curious mind listening in the dark. Wherever you are and whatever time it is for you now, you are part of that unfolding. The echo is still around us, faint but measurable, ancient but present, carrying the memory of a universe that began hot and dense and somehow, across nearly 14 billion years, became a place where it could wonder about itself. Sleep well, fellow traveller here in the afterglow.